and very good morning to Professor Du. Thank you so much. Professor Du, can you hear me?
Yeah, I can hear you. Thank you.
Thank you so much, sir. So, dear participants, let me introduce Professor Du. This is the sixth scientific lecture, and Professor Du from School of Pharmaceutical Science and Technology, Tianjin University, China, will deliver his very informative lecture on applications of hypervalent iodine reagents in in green organic reactions. So let me introduce Professor Du. Professor Du obtained his BS, that is in India it is called BSc degree. So BS in medicinal chemistry in 2001 and MS in organic chemistry in 2004 at Hebei University, China. He pursued his PhD in organic chemistry under the supervision of Professor Kang Jiao from 2004 to 2007 and stayed as a faculty member in Tianjin University after PhD graduation. In 2009, he was promoted to associate professor, and from 2011 to 12, he worked as a postdoctoral research fellow with Professor Richard P. Sung at the University of Wisconsin Medicine in USA. He was promoted in 2013 to professor in Tianjin University. Professor Du's research mainly focuses on synthetic organic chemistry and medicinal chemistry, developing novel synthetic methods, including the applications of hypervalent iodine reagent. Let me tell you, this is the one of the fascinating area of this organic synthesis, and Professor Du published more than 100 research papers on this particular field. And the Professor Du has published all total 130 research papers. All are in highly impacted journals, and was selected one of the highly cited Chinese researcher of 2020 by Elsevier. So with this short introduction, I again welcome you, sir. Thank you so much for giving us this opportunity to listen to you, and I think our participants will learn many things about the applications of hypervalent iodine reagent in organic chemistry from you. Over to you, sir. Thank you so much for giving us this opportunity. Thank you so much, sir. Now you please share your slide and you can continue your lecture.
Okay. So.
Yes, sir. It is visible. You please make it full screen. Yes, sir. Thank you so much, sir.
Yeah. So, firstly, I would like to thank Professor Banerjee for his kind introduction and also the invitation, providing me the opportunity to attend this important conference. It's really a great honor for me to report our work to all of you on this occasion. So today, the title of my topic will be Applications of Hypervalent Iodine Reagents in Green Organic Reactions. So as Professor Banerjee has mentioned, I came from Tianjin University, China. So as we all know, that green chemistry in nowadays is really very important, especially for our researchers working in the field of synthetic chemistry. So one important purpose for us is to prevent the generation of those waste, and at the same time try to use the safe chemical reagents and try to develop much more greener and more safer transformation reactions. So bearing that in mind, one purpose of our research is try to develop those novel synthetic methods for the synthesis of some heterocyclic compounds, but using the green synthetic approaches. So why is that? So I think it must have been known by all that the transition metal, especially those heavy oxidants, has generated a very severe environmental issue. They have been accumulated not only in the environment, but also bioaccumulate in those organisms. And it's really very troublesome and very difficult to have those heavy metal residues to be eliminated from our environment, and most importantly from our organism tissue. So the purpose of our research is try to realize the very useful transformations using some simple substrates, and to use the hypervalent iodine oxidants and realizing the formation of various heterocycles. So for such kind of transformation, we can avoid the usage of heavy transition oxidants, even the transition metal catalyst. So nowadays, we have already realized the synthesis of a series kind of heterocyclic compounds by using the oxidative coupling approach, rearrangement method, Cascade reactions, and even the asymmetric reactions for the synthesis of some chiral compounds. So on this slide, I just listed some representative examples that we have realized the synthesis in our group. So when we talk about the hypervalent iodine reagents, I think probably it will be better for us to take a quick look at the history of development of iodine reagents. So for iodine, it was isolated and from the ash of seaweed in 1811, and then in mid-1800s, organo iodine compounds have appeared and been used by the synthetic chemists. For example, in the Williams ether reactions, the alkyl iodide can be applied for the preparation of some ether compound, and also the alkyl iodide have been successfully applied in the Wood's coupling. And then in 1886 to the present, we can witness the development of the hypervalent iodine reagents. At the very beginning, the final iodine dichloride was discovered in 1886 as the first hypervalent iodine reagent. And after that, many hypervalent iodine reagents, for example, PIDA, PIFA, and even some hypervalent iodine 5 reagents, such as IBX and DMP, have been discovered and widely applied in various kinds of organic transformations. And even most recent decades, chiral hypervalent iodine reagents have appeared and have found wide application in some very useful asymmetric transformations. So why we would like to apply hypervalent iodine reagents in our research? So just now I have already talked about the significance of those heterocyclic compounds. We know it well that they are widely presented in the naturally occurring products, and also in those important pharmaceutical agents. They all bear various kind of heterocyclic compounds. And the CH functionalization mediated by the transition metal is a very powerful approach for the construction of those interesting heterocyclic compounds. However, when we come to take a look at the methods mediated by those transition metal approaches, we can find that although they can be applied only in catalytic amount, and they can realize high efficiency and atom economy of the transformation. However, still, in many occasions, the complicated ligand has to be applied, and most important issue is the residue of those transition metals. So how to solve the problem? We would like to realize the same synthesis of those heterocyclic compounds by using hypervalent iodine reagents, however, without the participation of any transition metals. And the features of the hypervalent iodine reagents include the low toxicity as well as the readily availability. Most importantly, the majority of those hypervalent iodine reagents are environmentally benign that means they cannot bring the problem of the pollution, environmental pollution, or even the bioaccumulation issue in our organism tissue. And there is a question, probably you may argue that for the transition metal mediated transformation, the transition metal can be used in catalytic mode. However, nowadays, the researchers have found that for the hypoallyl reagents mediated transformation, we can also use catalytic amount of the hypoallyl reagents, while at the same time using some cheaper terminant oxidant to realize a catalytic transformation under metal-free conditions. So the most commonly used hypoallyl reagents that have been applied in our research group include PIDC, PIDA, PIFA, as well as some other hypoallyl reagent listed here on this slide. So with the background introduction, next I would like to make a report about the transformations we have already discovered from our research. So for the first reaction actually discovered in our group, we found that by applying enamine compounds, compound 1, such kind of enamine compounds actually can be easily prepared by the condensation of cyanoketone, for example, with amine. And then by treating such kind of enamine compounds with PFA in DCM or DCE at room temperature, then we found the CN oxidative bond formation can occur and can realize the conversion of a series kind of enamine substrates to indole compounds. So if you are clear about the method for the preparation of indole compounds, you may see that actually for such kind of strategy is not so commonly used, mainly because the predominant strategy actually is using the nitrogen-containing arenes as the starting materials. However, for our approach, you can see we install the nitrogen atom at a relatively later stage, and finally we realize the CN bond oxidative formation by hypervalent reagents under metal-free conditions. So a series of indole compounds bearing different substituents can be achieved by the method. It is worth noting here that for the electron withdrawing group, we can have the thionyl group being replaced with the ester group or even the ethyl group. So because the reaction is very efficient and very fast, so we propose a radical mechanism for the formation of the indole products. We propose that intermediate A, an Ni bond intermediate, can be formed from the reaction of the substrate with PFA, and then it can, with the homolytic cleavage of the Ni bond, it can generate the nitrogen radical, and after the cyclization and also SET process, it can give the carbon cation intermediate F, and then with the elimination of a proton, we can obtain the indole product. And for this method, you can see that we actually, there is one thing that we need to confess, that is the substituent R2 on the substrate is indispensable for the reaction to occur. So with this result, we would like to see whether we can have the method being applied to the synthesis of some nitrogen unsubstituted indoles. That is, whether a substrate like just an enamine substrate with a free NH2 amino group can also be applied and can lead to the formation of the unsubstituted indole compound. However, when we came to study the reaction by using the same PFA, even at much lower reaction temperature, however, we found that the reaction gave a complex mixture. So with that, we came to investigate whether we can change PIFA, this PFA, into a less potent hypoiodine reagent, that is PIDA. So by subjecting the enamine substrates to the conditions of PIDA in DCE, also at a relatively lower temperature, we found that an intramolecular ionization reaction can occur and to give such a very interesting ethylene compound. So at the beginning, we were actually very concerned about the stability of the structure, maybe like many of you. However, we came to actually grow two crystals of our product and have two of them, being finely characterized using the X-ray crystal analysis. So the X-ray crystal analysis results can undoubtedly corroborate the structure of this class of compound. So by using the method, we can realize the synthesis of series of ethylene compounds bearing different substituents. You can see the cyanyl group here can also be changed into a ketone and an ester with the corresponding products being achieved in good to satisfactory yields. And that's a reaction mechanism we have proposed for this formation. So the ethylene compound can be achieved by using the approach. And you can see here that we also use the Ni bond intermediate. So that's quite important in our research, because we found that for a lot of transformations, we can propose such kind of a Ni bond intermediate. And it was noting here that different from the previous circularization pathway, this circularization happened between the this carbanion with the nitrogen atom, and then finally give a 3-member ring rather than a 5-member indole compound. So actually, such kind of ethylene compounds can also be found in some naturally occurring biologically active compounds. So the literature survey also can tell us that for the formation of such kind of ethylene compounds, they can be realized by using the classical Nibel rod, by using the vinyl azide as a starting material, or by the elimination reaction. And they can also be realized by some ring contraction from the 5-member ring or the 4-member ring, or some intermolecular reactions. However, for the direct intermolecular ionization reaction, actually it has never been reported. So our work can represent the first of such kind of transformation. And with the successful result of the CN bond formation mediated by the hypoiodine reagents, we would like to come to study whether the method can be applied to the CO bond formation. So also, again, starting from the enamine substrate 5, we will come to make a comparison of the substrate with the previous one. We can find that actually here, there is no substitution at this up position of the enamine starting materials. So by treating this enamine product, by treating this enamine substrate 5 with PFA in DCE just at 45 degrees, and we found that a very interesting oxidal compound can be achieved. And most importantly, we found that the trifluoromethyl group have been incorporated into the final product. So it really took us a longer time to have the compound being characterized, because at the beginning we never thought that the ligand of PFA, the trifluoromethyl group, can be incorporated in the final product. So for this method, actually is very useful, because by using such kind of a transformation, we can realize the synthesis of the oxidal compounds. So on one hand, the construction of the oxidal skeleton, and at the same time, the incorporation of the biologically interesting triphylomycyl group into the heterocyclic skeleton. So we also propose a reaction mechanism for the formation of the product. So due to the presence of the triphylomycyl group, because it's electron withdrawing, so we are unable to have these intermediate B or C being isolated from our control experiment. In actually all the cases, the intermolecular condensation happen simultaneously, and then to lead to the product fix the formation of the oxidal ring. So this condensation reaction actually happened very quickly. So with that, we thought whether we can have the method being applied to the synthesis of some oxidal product, but do not need the substituent to be the triphylomycyl group, because in some cases, although the triphylomycyl group is very good, it is being welcomed by especially the medicinal chemists, but for organic chemists, in some cases, probably is not necessary. So we would like to ask whether we can have the strategy being applied to the synthesis of some oxidal compound, but without the triphylomycyl group, but some other phenyl or aliphatic R1 group. So indeed, we actually was successful in realizing the conformation. We found that by using various kind of carboxylic acid, and this time we applied aldosyl benzene, another hypoallyl reagent, and then we realized the intermolecular CO bond formation between this enamine 7 with various kind of carboxylic acid, and to give product 8. So without the presence of triphylomycyl group, this intermediate 8 actually was stable enough to be isolated. So you can see we have many of them being isolated. And this one, just under reflux temperature, then the intermolecular condensation can occur to lose 1 molecule of water to give the corresponding oxidal product. So you can see we can also have the amino acid being applied to the transformation, and can realize the formation of compound non-S. So here you can see the presence of the oxidal skeleton as well as the residue of an amino acid will make it a very useful building block for the biological studies. So for the previous examples, you can see we have realized the CN bond formation as well as the CO bond formation mediated by the hypoallyl reagent. So we then have a question whether we can realize the carbon-carbon bond formation by using the hypoallyl reagents without the participation of transition metals under completely metal-free conditions. So this transformation, you can see, has already been reported in 2008 by Professor Gorius. They applied palladium and copper and realized a direct carbon-carbon bond formation from such kind of an enamine substrates. So we would like to ask a question whether we can apply the same starting materials but realize the same carbon-carbon bond formation just in the presence of hypoallyl reagents under metal-free condition. So that's our research plan at the beginning, and finally we found that indeed the transformation worked very well. We can realize the conversion of such kind of an unsubstituted enamine into the indole product through an oxidative carbon-carbon bond formation just by using hypoallyl reagent PETA without the participation of any transition metals. So a series of indole compounds can be obtained. So actually that this work actually realized our wish, at the very beginning, because we really wanted to prepare the nitrogen unsubstituted indoles by our hypoallyl mediated strategy. And for this transformation, you can see we can realize the synthesis of a series of nitrogen unsubstituted indole compound. And here, the electron withdrawing group, the scope of the electron withdrawing group is even bigger. We can also have such kind of 3 nitro indole compounds being prepared by the micelle. And that's a reaction pathway we have proposed for the formation of the indole products. So here you can see the NH moiety in the substrate is quite necessary for the formation of such kind of an Ni bond intermediate. So without this NH moiety, for example, we actually have carried out the control experiment. If it's not NH, if it's a substituent, a methyl group here, actually this reaction cannot occur. So a very crucial electrocyclic ring closure process happens during the transformation, which is crucial for the carbon-carbon bond formation. So we have also realized the carbon-carbon bond formation between an sp2 carbon from an aromatic ring with a sp2 carbon from an aldehyde. So for this transformation, we applied the substrate twice and have it treated with PIDA, and also in the presence of some radical initiator BPO, we can realize the direct carbon-carbon bond formation between these 2 moieties. Actually, we have to admit that for this transformation, it's really not so easy. So you can see here, 100 degrees, the temperature 100 degrees needed. So that is actually rarely seen in our previous transformation. For the previous coupling reactions, most of the time the reaction can occur at room temperature or lower than 60 degrees. So by using this approach, we have realized the synthesis of the corresponding acridone product, so in moderate to satisfactory yields. And for this transformation, we propose a radical pathway. Most importantly, is the formation of such kind of acyl radical, and then the formation of the carbon-carbon bond and the further oxidation to give the final product. So also with that, we came to think whether we can have the micelle strategy being applied to the heteroatom bond formation. So inspired by this work published in 2012, so you can see here, it's also a hyperiodine mediated CN bond formation. For this transformation, you can see that the sp2 carbon of the aromatic ring has been connected with the nitrogen atom of this imine moiety to give such kind of imidiazole product. So we would like to see whether we can have this carbon being replaced with nitrogen, and to apply such kind of substrate 14 and have it treated with hyperiodine reagent, and to give an N bond forming reaction and give such kind of triacyl product. So we prepared such kind of substrate 14. Actually, they can be easily achieved using the aminopyridine as the very starting materials, and have this one being treated with PFA in this HFI PS solvent at room temperature. Then a very convenient NN bond formation can occur, and to give the corresponding triacyl pyridine product. So the yield of all the reactions was generally high, and most importantly, actually, we do not need a silica gel column work to purify and isolate our product. Just a very simple filtration and then evaporation can give the product in a very high yield and a high purity, which is pure enough to be characterized by the NMRs. And also that's a reaction mechanism we propose for the formation of the product. And once again, the formation of an Ni bond intermediate is quite crucial for the final ring closure process. So with that, I would like to move forward to the second part. The first part is mainly about the oxidative carbon reaction. Second part is about the cascade reaction. So we have also applied the strategy of those bond forming processes to the formation of some spiral heterocyclic compounds. So here we have applied the diphenyl malonamide starting material 16. By treating this one with PFAS at room temperature, we found that the carbon-carbon bond formation can happen twice here, and then to give the spiral oxo-indole products. So here you can see by adopting the strategy, we can realize a metal-free oxidative carbon-carbon bond formation twice, and most importantly, it can realize an intramolecular spiral circulation process, and to give those very interesting spiral oxo-indole products. So most importantly, you can see from the example of 17E, we can realize different substitution on the two aromatic rings, and also from 17H, you can see we can realize the formation of products bearing different substituents on the two nitrogen atoms. So that's the reaction pathway we have proposed for the formation of our spiral heterocyclic compound. So here you can see for this intermediate A, we use the OI bond intermediate, and then from here we realize the carbon-carbon bond formation of the first carbon-carbon bond formation, and to give intermediate B, and then it will continue to undergo the further with the formation of the first ring. It will continue to react with the second molecule of PFAS, and then to realize the second formation of carbon-carbon bond. So we were very happy to see that our work, gained the attention from Professor Suno, and he actually carried out a very delicate computational studies about our transformation. So according to his delicate computation, the result indicated that at the very beginning, indeed, it was the OI bond formation. But however, this OI bond intermediate can undergo a rapid 1,3 migration, and then to give a rather stable CI bond intermediate. And then from this CI bond intermediate, it will undergo the further carbon-carbon bond formation twice, and then to give the final spiral oxo-indole product. So here we would also like to thank Professor Suno for carrying out such a wonderful computation study about our work, and then provide further insights, further highlights to the reaction mechanism we have proposed at the very beginning. And that's our previous work. We found that for such kind of a substrate A, when it was treated with PFAS, the carbon-carbon bond formation can occur. However, in the presence of the PFAS, the intermolecular CO bond formation can also occur, and to give a hydroxy-indole oxo-indole product C. So also we found that when we come to treat the starting material D with PFAS, that is to have this one subjected to the same reaction conditions, we found that it cannot give this hydroxylated product F. That means during the process, it was actually the carbon-carbon bond formation happened first, then the second hydroxylation reaction occurred. And also we came to find a very interesting paper published by Professor Fan from Fudan University in China. He found in his work that by treating such kind of starting material G with with PDA, then an intermolecular CO bond formation can occur, followed with the next intramolecular CO bond formation. Then based on our own results, as well as the outcome from Professor Fan's work, we would like to ask whether such kind of a starting material 18 can undergo the carbon-carbon bond formation first, give intermediate G, and then the further CO bond formation, and then to give the spiral compound 19. So that is our proposal. Then we came to prepare the starting material, actually not so difficult, and have this one being treated with PFA in DCI room temperature. Indeed, we found that the reaction gave our expected spiral oxo-indole products 19, and we can have the method being applied to the synthesis of series of such kind of spiral furrow oxo-indoles in very good to satisfactory yields. And then we carry out some control experiment to elucidate the reaction mechanism. So here you can see first we have the hydroxy group being removed from the substrate, try to see whether this one can give the carbon-carbon bond forming product. However, to our surprise, this reaction didn't work. Then we have the final ring in the substrate being removed and prepare this starting material C and have this one being treated with PFA. And to our surprise, we found that the CO bond forming product D can be achieved. Then for our reaction, we carry out the reaction under various conditions. For example, for this one, we carry out the reaction at -20 degrees. Just hope that we can find these CO bond forming intermediates. However, in all the cases, we cannot have this one being isolated and characterized. And in all the cases, what we have achieved is 19A product. However, for a special case, when we come to use this 18D, we carry out the reaction at -20 degrees. We found that indeed we can find this intermediate E being isolated and have it finally characterized. And after having this obtained in hand, we have it treated with PFA again, and then it can undergo the further carbon-carbon bond formation. So based on the result from this control experiment, that we have to revise our reaction mechanism. When we proposed at the very beginning, we thought it was the carbon-carbon bond formation happened first. But the result clearly indicated that actually during the process, it was the CO bond formation that happened prior to the carbon-carbon bond formation. So then we also applied some such kind of alkane amide starting material 20. And we have it treated with PFA, and we found that it can give such kind of spiral heterocyclic oxo-indole products. And you can see very interestingly here, you can see the purple carbonyl group. Actually, this carbonyl oxygen comes from not come from the oxygen in the air, nor it's from the water in the solvent. Sometimes have some residue there. It's actually come from the ligand of this hypervalent reagents. So we can also have the nitrogen atom there being replaced with the oxygen, and to prepare the analogs of those spiral oxo-indole products. So also with that, we would like to investigate whether this substrate A1 can also be give the corresponding oxo spiral heterocyclic products, because in many occasions we can see that the alkane group here plays a similar role of such kind of dicarbonyl group. However, when we have this one being treated with a hypervalent reagent, we found that this one A1 actually give messy results. Then we would like to see whether we can have this carbonyl together with neighboring CH2 moiety can be replaced with the alkane moiety, and try to investigate whether the substrates 22 can undergo some interesting spiral lydation process and to give, for example, such kind of spiral heterocyclic compound 23. Then we have the starting material prepared using those known methods, and have this one being treated with PFA in DC at the 0 degrees. We found that the CN bond formation, carbon-carbon bond formation can occur to give the corresponding two spiral pseudo-endoxial skeleton. so the corresponding products can be obtained in satisfactory to good yields. And most importantly, actually, you can also see that actually there is a pro-chiral center in those products. So again, we would like to carry out some control experiments to understand, have a better understanding of the reaction mechanism. So first, we have this 22 being treated in the absence of the hypervalent iodine reagent, just in the presence of the TFA, to see whether the indole ring can be formed. Actually, we didn't see the formation of such kind of indole product. And also, we have the this starting material B being treated with the hypervalent reagent to see whether the reaction, the CN bond formation, just can happen between the nitrogen moiety with the alkane moiety. However, to our disappointment, we found that actually the hydroxylation occurred on this electron-rich renin ring. And we also apply the other alkane substrates to the standard reaction conditions, and we found that actually in those three different cases, no reaction occurred. So based on the experiment, we actually propose two possible pathways for the formation of our products. So first one is the CI bond intermediate, and the other one is the OI bond intermediate. So I think due to the limit of time, I do not need to have an elaboration on the reaction mechanism. So we would also like to share with you that actually such kind of chiral iodide actually has been applied in those iodine-mediated asymmetric transformations. So at the very beginning, I talk about the use of such kind of aryl iodide as in a catalytic amount, and then using some cheaper terminal oxidant, for example, MCPBA or hydrogen peroxide as the terminal oxidant, and to realize those asymmetric transformations. So these are the three transformations that have already appeared before our research. So you can see by using different kind of chiral aryl iodide, Kita and Ishihara from Japan have realized the spiralization during the process. You can see it's the CO bond formation. And also, I think you should be familiar with this transformation, because this transformation, the original type was actually discovered in our group. Then Professor Gong from China, they realized the asymmetric transformation of this double carbon-carbon bond formation. So they have applied such kind of chiral aryl iodide as the chiral catalyst. Then in the presence of those cheaper oxidant, realize an asymmetric transformation. So actually, inspired by the previous work, we have such kind of readily available starting material 24A. Also, we screened actually a series of aryl iodide, and we finally found that 20D is the same one that has been applied by Professor Gong. Is a good aryl iodide for our transformation. So we also realize the asymmetric transformation, realize the synthesis of such kind of spiral also indole products. So during the process, you can see not only the carbon-carbon bond formation has occurred, and carbon oxygen bond has been realized. So we have the method being applied to the synthesis of a series of chiral spiral hydrostatic compounds. And we also have one being isolated and being characterized by the actual crystal analysis, which indicates that the absolute configuration of those products can be obtained. So we also carried out some control experiment to understand the reaction mechanism. First one, we would like to know it is the CO bond formation or the CC bond formation that happened first. So by doing such kind of a control experiment, we can see that it was actually the CO bond formation that happened prior to the CC bond formation. And then next, we would like to understand which step determines the generation of the initial selectivity. So we also, you can see we have for P being subjected to the reaction conditions, and we found that actually this intermediate A can be obtained in cannot be in natural selectively formed, just to give a rhythmic mixture. So with that, we propose a transition model for the generation of the chirality of our product. And finally, we propose that it undergo this pathway from this transition state. You can see the light steric repulsion here between the two bulky groups, and finally all the products can be determined to be the R configuration. So also I would like to introduce you about some other interesting rearrangement reactions. So just now what we have talked about is the cascade reactions. So actually our research also originated from those transformations mediated by the palladium. For this transformation, you can see starting from such kind of aniline amide starting materials, you can see the 5-membered oxo-indole products have been obtained during the process. It is the carbon-carbon bond formation, and whether it is we can adopt two pathways. One is the CH activation or the olefin activation by those palladium catalysts, but finally you can see the product can realize carbon-carbon bond formation to give a 5-membrane such kind of product. So we would like to inquire whether we can have the same substrate being treated with hypervalent reagents and to realize a similar carbon-carbon bond formation, because such kind of transformations have already been previously been reported by Professor Thomas Worth from Britain. So, but when we come to treat such kind of starting material with our hypervalent reagent, we actually found that the carbon-carbon bond forming products cannot be formed. What we have obtained is such kind of an interesting carbon-carbon bond forming, but at the same time, this terminal final group have shifted from this position to this position neighboring to the carbonyl group. So the structure of the product can be corroborated by the X-ray crystal analysis. So that is the result we have achieved from this transformation. We can have this method being applied to the synthesis of series of such kind of 3-aryl quinoline owns products. And also, most importantly, we can have the method being applied to the synthesis of this important intermediate 28L, because this one can be used as the useful starting with intermediate for the formation of some natural products. And that's the reaction mechanism we proposed for the formation of the products. So you can see it is from this intermediate D that realize the migration of the final group. So actually, when the paper was published, we also would like to continue to understand the reaction. So here you can see different starting materials when they have the different. You can see the substrate type is pattern is different here. During our transformation, we found that the aryl group, the substituent that is at the trans position with the amide moiety migrate during the process, while the other one didn't migrate at all during the process. So if we actually propose a reaction mechanism here, so from this intermediate DB, you can see that actually there should be no selectivity for the migration of AR or the final ring. So with that, we think we have to further carry out studies to understand why during the process only the trans aryl substituents have migrated. So we collaborated with some computational scholar, and they proposed a reasonable reaction mechanism for us to understand the reason why during the process it is the trans aryl group that have happened. And also, I would like to introduce another rearrangement reaction here to you. So at the beginning, actually, we would like to see whether such kind of substrates can undergo a CN bond formation and to give such kind of diazepine products. But during the process, very interestingly, we found that this one can be converted into this diazepine 2-ons product in this form. During the process, clearly you can see aryl coupling have happened, rearrangement reaction have happened, and also during the process there's a ring closure. However, for the previous formation of such kind of products, it was from such kind of aryl starting materials. But for our transformation, you can see we can have the two final ring being linked by a amide bond, and then can have this one being treated with hypervalent reagent to realize the synthesis of a series of diazepine 2-ons as well as its analogs of vapine ons. So we also can have the amide moiety being replaced with an oxygen atom and have it being applied to the synthesis of the corresponding analog. So I have just now mentioned that point. And that's a reaction mechanism we have proposed for the formation of such kind of 7-membered heterocyclic skeleton. However, it's really very difficult for us to have this intermediate D being isolated and characterized. But it doesn't matter, we can have this intermediate A being isolated. And when we have this one isolated and have it further treated with triple boron ether, then it can undergo the rearrangement to give the corresponding product 13-1. What does that mean? That means that reaction mechanism we have proposed for the amide, for the substrate bearing amides is actually reasonable. However, this when this paper was published and then was being highlighted by Synfax, the expert said further investigation on the reaction mechanism should be carried out. Then we came to did this research and then found that for such kind of a substrate, it can actually undergo the migration. So during the process, it's the aryl group that's migrating. And also for this example, it has been published on tetrahydrogen lighter. So in the presence of the PTSA, for this substrate, also the aryl group that is being migrated. So that's understandable because during the whole process, it should be the electron-rich aryl group that migrates. And this one, although the author didn't carry out the experiment work, but they proposed from a theoretical point of view that for such kind of substrate, it should be the aryl, this aryl ring that migrate and to give the corresponding 6-membered heterocyclic products. However, for our transformation, we thought that there is a problem there because if this proposal is correct, then for our proposal, probably it will not happen and then give the corresponding 7-membered heterocyclic skeleton. So then we thought for our transformation, because that have already been approved by the results from the paper published on Water Committee. So according to the results from the heterocyclic skeleton heterocyclic paper, then the migration should happen and to give this F5C. But according to our result, then it should be this amide moiety that migrates and to give this corresponding 5F product. Then which one should be correct? We need to carry out a control experiment to understand further the reaction mechanism. So then later on, we found that by having such kind of substrate being subtreated, treated with the Lewis acid, we got this L5 prime and have it treated with having it being methylated and to give this G5. We can have this one being characterized using the X-ray crystal analysis, and it is indeed this one. So that means that actually during the process, it is not the aryl group that is migrating. It should be the amide, this carbide moiety that is migrating during the whole process. And that one can also well support the reaction mechanism we have proposed in our previous work. And last, I would like to share a piece of work that we have recently realized. Actually, it's a kind of rearrangement reaction mediated by the hypervalent reagents. So by treating such kind of carboxylic acid 32 with iodobenzene in the presence of some alcohol solvent, then we found that we can actually build such kind of lactone. So most importantly, you can see here the final ring has migrated. So we can have the method being applied to the synthesis of a series of such kind of methoxylated lactone products. Most importantly, we can also use the deuterated methanol, which is a solvent that being used in NMR analysis in our transformation and to realize the synthesis of corresponding products. So that's a mechanism we propose for the formation of such kind of a rearranged lactone together with alkoxylated products. So for this method, the key features include exclusive 1-2 aerial migration lactonization, and also we can have this deuterated methanol applied in this one-part approach, and also in all the work I have talked about today is totally metal-free. So if you are interested about the hypervalent reagent-mediated rearrangement reactions, you can come to read this review paper, which we have contributed to chemical communications recently. And with that, I think I will come to the make a quick summary about my presentation today. So for the first part, I talk about the oxidative forming reactions mediated by hypervalent reagents. I presented altogether 6 examples of the formation of some heterocyclic skeletons. And for the Cascade reaction, we realize the synthesis of a series of spiral heterocyclic compounds. So during the process, you can see it's actually the oxidative carbon-carbon bond, double carbon-carbon bond forming, or carbon-carbon bond forming reaction together with the carbon heteroatom bond forming process. And also we have realized one asymmetric transformation using the chiral aryl iodide, and also we have found some interesting rearrangement reactions mediated by hypervalent reagents. So with that, I think I'll have to come to the end of my talk. So first, I would like to thank students for carrying out the recent work, the corresponding work, and also I would like to thank Professor Richard Singh at the University of Wisconsin Medicine, and also a very good collaborator, Professor Wu Ping Tang there, and would like to thank the financial funding from our university and from our government for their financial support. So last, please allow me to make a very simple introduction about the city I'm living. So actually I'm from Tianjin. Tianjin is very close to Beijing, the capital of our country. So if you take a high-speed train, it will just take you about 30 minutes to travel from Beijing to Tianjin. So actually it is the city transportation is very convenient. It's actually the transportation within the city that's really actually time consuming, because you might encounter a traffic jam. And our city is international metropolitan, so the transportation is travel is very convenient to Beijing or even to Shanghai. So that's the campus of our university. So just here, I would like to share that with you. So if you happen to be in China, you are welcome to visit our Tianjin University. So that's all of my today's presentation, and thank you very much for your kind attention. Thank you.
Thank you so much, Professor Du. Thank you so much for your very lucid and informative information. I always love to hear from you, because you every time you it's like a class room teaching. You presented so nicely, and you make every new bond with a new color, and you showed all the mechanism. That is a very beautiful techniques. I always love to hear from you. Thank you so much, dear participants. If you want to, Professor Du is actually contributing one chapter in our edited book, which I am editing with Professor Bani. So that review, from that review of that book chapter, you can learn many things regarding this hypervalent iodine reagents and reactions that will soon published in physical science reviews. So I'm once again thank you, Professor Du, for your valuable time and sharing your achievements with our participants. Now, dear participants, there is a very short time, so I'm requesting that, yeah, Dr. Rakesh Chow, you please unmute and start your video if you have any question, because you raise your hand.
Yes, sir. Sir, very good morning to all of you, all the participants and respected sir. Sir, my question is related to the topic taught by sir, that is the synthesis of acridone derivatives via carbon-carbon bond formation. He has taken BPO as a reactive intermediate, and the product is also BPO. So my question is that how it comes, sir?
So actually, that BPO, we have that one applied as a a radical initiator, because we think the reaction proceed radical pathway. Without this BPO there, this carbon-carbon bond formation actually didn't occur. So generally, for such kind of carbon-carbon bond formation between the aromatic sp2 carbon with sp2 carbon from aldehyde, that's actually not so easy. So for our transformation, we found that this BPO is really indeed a very important for initiate the radical pathway. So that's also give us highlights actually transformation mediated by hypervalent iodine reagent probing, it involves the radical pathway. So that's a very good question, and thank you very much.
Thank you, Professor Du. Now, there is another one person, Ashish Mathur. Please share your, please start your video and please ask your question.
Yes, sir, it is visible.
Yeah.
Good morning,
Yes,
yes. Good morning, all of you. Thank you very much, Professor Du, sir. I fully enjoy your lecture. You explain everything in details. It's easier for me to understanding this type of mechanism. And sir, just one inquiry. Could you explain like iodine 3 reagent like MCPBA in iodobenzene? So how much amount MCPB and iodobenzene in situ, and how would you addition to this process and produces to another I3 reagent?
Yeah, that's a very good question. So we come to use a catalytic amount of hypervalent iodine reagent after the reaction. Actually, this hypervalent iodine reagent will generally be converted into final iodide. Then the final iodide can be regenerated to hypervalent iodine 3. Final iodide is hypervalent iodine 1. Actually, not hypervalent, that's iodine 1. But for the hypervalent iodine, there are 3 or 5. So the final iodide can be converted, can be oxidized by MCPA to hypervalent iodine 3. Then it is actually this hypervalent iodine 3 species that is, enable the oxidative coupling reaction, for example, of that transformation. But that is true. In some cases, you have to pay attention to one concerning issue, that is, do not let MCPBA to oxidize your substrate. Yeah,
yes, sir.
You have to delicate control the reaction parameters there. Yeah.
Sir, another question. You maximum slide you saw DCM or HFIP or PETA in low temperature. Any role in low temperature?
You mean lower temperature?
Yes, a maximum reaction show or CC bond formation or CH bond formations in low temperature, PIDA or HFIP in DCM solvent in -20°C. I think so. Any role of this low temperature?
Yes. So for sometimes it depends. Actually, I think we should consider the issue from two aspects. First, how reactive are your substrates? Sometimes, if your substrates contain some, very reactive functional groups, for example, OH or NH2, then we can regard your substrates very reactive, very delicate. So you need to control the reaction in a very delicate way. You need to use some less potent hypervalent reagent, and then you need to consider the solvent. In most cases, DCM or DCE, those hydrogenated solvents very good, but sometimes they are not, they cannot activate the hypervalent reagent. You may also be using some, for example, trifluoroethanol. Those fluoro-containing solvents, they can actually promote the reaction to occur. So also you need to, tune the reaction parameters. For example, sometimes lower the reaction temperature to -20 and sometimes even -70 degrees to lower the reaction overall reaction activities. Yeah.
Yes, sir. Thank you, sir.
Thank you so much, sir. Thank you so much. Actually, next speaker, Swapandeep sir, is also with us, joined with us. So thank you so much, dear participants. There are so many research scholars are there. So I'm requesting you, if you are interested with in future, you want to work with hypervalent nitrate reagent, then you can apply to Professor Du for your postdoctoral research, or you can apply for your doctoral research also. So this is a good opportunity for you people to you can go to your sir's page, or you can directly contact with him. So thank you so much once again, Professor Du. Thank you so much. Now I'm requesting, thank you so much, sir. Now I'm requesting Swapandeep sir, can you please unmute yourself and you start your video. Swapandeep sir, can you please hear me?
Yeah, sure. Hello, thank you very much.
Thank you so much, sir.
So had a night. Yeah.
For your as you have agreed to give your valuable lecture for this platform. Sorry for it is around 7 minutes late. So let me just a minute. So this is our 7th scientific lecture. Professor Swapandeep Singh Chimni sir from is a professor of organic chemistry, Department of Chemistry, Guru Nanak Dev University, Amritsar. He will deliver his lecture on the topic bio-inspired organocatalytic enantioselective carbon-carbon bond formation. So let me introduce Professor Chimni sir. Professor Chimni received BSc in 1984 and MSc 1985 and PhD in 1991 from Guru Nanak Dev University. He is currently holding the position of Professor of Chemistry at Guru Nanak Dev University, Amritsar from 1990 to 1992, he was a lecturer in applied chemistry at NITJ Jalandhar, where he initiated his research on biocatalysis. Recently, he is the professor of chemistry from GNDU, and he published more than 120 research publications. All are in reputed journals with high impact factor. Many times his research cited in the front page. And Professor Chimni produced several PhD scholars and guided so many MSc students also. Thank you so much, sir, with this short introduction, because I don't want to waste your time further. So thank you once again for giving us this opportunity to hear from you, sir. Thank you so much. So now you please start your lecture. Your slide is already visible in our screen. Thank you, sir.
Okay, thank you, Professor Banerjee, for giving a nice introduction and giving me this opportunity to interact with the research scholars and other students through this international conference on green chemistry, recent trends in green chemistry, as you have named it. Well, at the beginning, I would like to tell you that I'm going to talk about organo-catalyzed reactions or organocatalytic reactions as they are referred to. So, and when we talk of catalysis, I just want to link it to your conference. Then when we talk of catalysis, we talk of green chemistry. And because catalysis is one of the 12 principles of green chemistry. So from that point of view, my lecture is relevant to the title of the conference that you are organizing. Okay, so I will try to link things with nature. So how humans learn from nature and then devise things, and you can see from the very first slide that I have, there's some depiction of all these things, and I'll just quickly take you through the nature-inspired designs that are there that we are using day in and day out, and then I'll take you on to the chemical aspects, how certain reactions we have learned from nature, and how nature has inspired us. That is why the word bio-inspired. So first, I'll try to talk about what is inventions inspired by nature, which are referred to as biomimicking. And and if you look at this, there's a wind turbine that has been designed on the design of the fins of the whale. This actually design of the turbine helps in reducing the drag and the noise, and it increases efficiency. Then second, I hope all of you must have heard about bullet train. There was a lot of talk bullet train being introduced in India also. So this Japan's Shinkansen bullet trains, nose were actually modeled on the sharp beak of the kingfisher. And the kingfisher can enter water without any ripples being created in the water, a splash. And the bullet train's engine nose was then designed on that, so as to reduce the air drag and noise that was associated when it was moving at a high speed. So that helped in reducing the noise of the train, less power and high speed. So that's how, well, in fact, there's a story behind it that the engineer who was working on this model of this train actually was facing this problem of high noise and a lot of air currents. So he was a good, I mean, he loved watching birds, and he was on a trip of bird watching when he noticed this. And then he came out with this idea, and this whole new thing was designed. Then another two examples, maple seeds. You can have a look at this. This is a maple seed. The maple leaf is in a circular flight, and this inspired the design of a new drone with the rotors which mimic these maple leaf flight or maple leaf seeds, which whirl in the air as they fall. So, another one is candy-coated vaccines. You have heard about vaccines in recent times a lot. And it's very important that the vaccines should be stored at very, very low temperature. And if one needs to store them at room temperature, something else has to be done. And this idea actually was there or already there in nature. I mean, scientists have been using, and this has come from a very, very small creature, which is an 8-legged micro animal, in fact, which is shown here. And it lives in water. And if there's no water, it just survives, and it can survive over many years till it is again it is again put into water, and that inspired the scientists to discover what is the secret behind this, that this micro animal can survive under adverse circumstances and under climatic conditions. And they found that there is a covering of some polymeric carbohydrates. So that is why the word candy. So learning from that, we can they have designed certain materials which can be used to cover the vaccine, and once inside the body, the outer carbohydrate cover can dislodge and it can release the vaccine. So that can help in preserving a live vaccine without refrigeration. So these ideas have come from nature itself. Then this is a building in Harare, Zimbabwe, and it was constructed based upon the molds of simple. Okay, so you might have seen this sometime in while going into the countryside. You might have seen this termite molds, and that is or termite houses, mounds or houses, as you can call. And the design of this is such that it is based upon the mounds of the termite, and it keeps this building at a normal temperature. So you don't need any air conditioning for it. So it can be kept at a normal temperature. Just the design ensures that there's a flow of air in it, and the cool air flows in, and the hot air just flies about. Then this is something all of us are quite familiar with. The next one is Velcro. So this invention was inspired by the way plant burrs stick to the dog's hair. Actually, again, this was a French engineer, in fact. He went for a walk, and his dog was like having so many burrs on its hairs, and then he put it under a microscope to see why it is so tightly sticking to the hairs of the dog. So these plant birds, then he worked on this and maybe more than 10 years and came out with this idea of Velcro, which nowadays is very commonly used. And they are very, very tiny hooks that would catch onto the loops of the hair or even the clothing. And I hope some of you might have experienced this also. Then lizards, you're all familiar with lizards. Gecko lizard feet, the feet of the marble velvet gecko have inspired a range of technological solutions to holding on to the vertical surfaces. So, and this is how it holds on, and there's a very fine fibril fibers, very fine fibers which have these adhesive properties, and they have been idea has been taken from it to make surgical adhesive for better healing and drug delivery. So just see, and it can also be used for other purposes. This is just one example which I'm referring to. Then last example which I want to share with you is this small insects, which actually harvests water. It lives in a desert and harvests water, and which comes on its back, and then that droplets flow down to towards his mouth, and then he can drink that, because this is Namim desert beetle. So the back, studying the structure of the back of this beetle actually led to the development of a material which is shown on this side, which could be used to collect water in a desert area. So nature has inspired. I mean, these are just few, just to highlight the point that nature, if you watch nature critically, you can really get some ideas, and those ideas can be transformed into useful materials. And these are certain technological developments that has actually helped in improving the quality of human life. So from here, just giving you a start from here, I would like to take you on to some chemical transformations or chemical synthesis that has been inspired from nature. So this is one. Okay, the artificial synthesis, photosynthesis, in fact. So if you have a look, this is the diagram where we are trying to show that how the photosynthesis occurs. And this is an artificial photosynthetic setup. So it is basically based upon harvesting light energy and then try to use that energy for some useful purpose. And the device actually consists of nearly 450 leaves, which are actually tubes made of periodic organosilica and light absorbing biphenyls. So and these are placed here, and this is how somehow it looks like. Okay, so it looks something like this. And what you see, actually I'm trying to adjust these the side ones, but anyway, These complexes were then linked to 5 connected ruthenium metal sticks, which was transferred the light energy harvested at this very point, and that directly to the central ruthenium sphere, which can then be used for a different purpose. So this mesoporic organosilica is the one which is then used for harvesting this. Okay, so these are artificial photosynthesis. This is another example, but here we are trying to talk about bio-inspired H2 production. So here also, if you can see this, the synthetic catalyst actually, such as water oxidation catalyst based on design of the natural photosynthesis 2 manganese clusters, or hydrogen activation catalyst based on design of natural reversible iron hydrolase, iron hydrogenase hydrogen clusters show promise in mimicking many of the catalytic properties of these their natural counterparts, and this is one example which has been done. And these nanostructured materials have been used for bio-inspired hydrogen production of the catalyst. Hydrogen production catalyst has been used as the hydrogen production catalyst. Just taking you to another example, that is fuel cell, same cathodic reaction that is seen in mitochondria and the same fuel cell. So this is a small device which uses that knowledge of mitochondria to carry out the reaction which is performed in the mitochondria, which is a fuel cell. So the oxidation reduction taking place in the mitochondria is exactly the same in standard cells. So using these several enzymes and other earth abundant material elements, the mitochondria converts this electrochemical potential to biochemical work. And this has been used in these examples which we are highlighting here. Okay. So conversion of this electrochemical potential work to meeting human needs, that is, we're producing water here. Okay. So another example, and then I'll move on to the work that I am supposed to present you. So DNA-based gating membranes and nano devices have been developed based upon DNA, and the molecular scale devices use DNA nanostructures have been engineered, and they show to have capabilities. They can use as scaffolds or templates for further assembly of other materials, and also robotic movement and molecular transport, then transduction of molecular sensing to provide drug delivery. So many things in there. So then one more example is about bio-inspired chemistry based on minimalistic pseudopeptides. So simple pseudopeptides can be properly designed as promised bio-inspired molecules displaying functionalities related to those of peptides and proteins. So these are some minimalistic pseudopeptides which have been introduced, and they can be used as catalyst, and they also show host gas properties, and so can be used for catalytic purposes. Okay, so moving on from here to where I actually want to take you on. These are just few examples. Bio-inspired design of the catalyst. How can we design catalyst? So that means the idea which I've tried to build up till here is that you can learn a lot from nature. And if you're a good observer of nature, you can really learn a lot from it. And now moving on to, can we learn from biological processes to design the catalyst? Yes, we can do that. And mimicry of hydrolytic enzymes by small organic molecules, then mimicry of polyketides synthase, and mimicry of epoxide hydrolysis for the design of double hydrogen bonding organocatalysts. This is what we'll be talking about next. So if serine proteases are enzymes that are involved in hydrolyzing the peptide bonds in proteins, and the serine serves as a nucleophilic amino acid at the catalytic site of the enzyme. So if you just look at here, and the examples shown here, some of these proteases are trypsin, chymotrypsin, subtilissin, and these are the ones which can be used. And there is NS3-4A, which is also a protein, serine protease, which is present in hepatitis C. And that is important in viral maturation, if one can look at this how. So these serine proteases actually have a triad, which is serine, to which the substrate binds. Serine is actually catalytic, chemically catalytic, the catalytic unit that it is. Then histidine, which has the ability to donate and accept protons. Aspartate, which has the ability to accept protons. So you can have this histidine and aspartate. So this is called a catalytic triad, which is involved in these transformations. Then the mimicry of the active side of this serine protease was this small molecule which was developed by Ricci actually, and this is just a representation of the serine, and then there's histidine and aspartic. So this is the catalytic triad, but there's activation by these amide NH of the carbonyl of the amide bond. So what they were trying to put at, you need an oxyanion hole, which is here, and and there's a nucleophile which is quite equivalent to the serine OH, and the journal base, which is quite equivalent to this histidine nitrogen, which has been incorporated into this molecule. So this catalytic actually mimics the active site serine protease, where the thiourea group of the catalyst acts as an oxyanion hole and stabilizes the carbonyl compound in transition state, in similar fashion as the natural enzyme as shown in this structure. So do we have an example? Yes, we do have an example where this has been done. So this is actually referred to as a trifunctional organocatalyst, which has been used for transesterification reaction like this. And it has nearly 100% conversion in 1 hour. The catalyst is this thiourea catalyst 1, and 1 mole% of this is used. But if we use catalyst B, which is a urea catalyst, it was interestingly found that by this group that the same transformation, esterification transformation could be done in 30 minutes. But they moved on to a lower percentage of the catalyst, and they found that it takes longer time as it is expected. So so one can really decide about, but one thing was what they observed was that it is the urea catalyst which was actually giving a better results than the thiourea 1. Normally thiourea 1 is found to give that. Then another polyketide synthase makes up a diverse phylogenetic groups which starts with acetyl coenzymate to form linear chains. If you had a course on biosynthesis, then probably you're all familiar with the polyketide biosynthesis. So this is quite commonly seen in fungi, bacteria, and particularly the actinomycetes and sea slugs. So, and a lot of these bioactive molecules, which are medicinally active also, are obtained from nature. And these are the results of polyketide synthase. So it works like this, but although I'm not focusing on the whole of this system, but what I want you to look at is that there is a step which involves decarboxylation. There's a carbon, and this malonyl acyl carrying protein, and this decarboxylation occurs, and that leads to the chain elongation, and this intermediate enolate actually adds on to this and the carbonyl, and it leads to the chain elongation. So this is the general mechanism of polyketide, and if we just see how we can use this idea for making new catalysts, and the new catalyst could be made in this term. This was also introduced by Ricci. So a mimicry of this polyketide catalyst, he worked on this cinchona-based thiourea catalyst, and he found that one could do this similar sort of a decarboxylative addition reaction, and this was actually addition to a nitroolefin that he tried, and it was successful. The idea was to develop this catalyst based upon the polyketide mechanism, one of the enzymes of polyketide synthesis, which was then involved. Then Venemer also actually introduced this earlier, was the first to report this decarboxylative addition of malonic acid half-thioesters to nitroolefins. And this was the reaction that they came up with. And it was giving quite high yields and good enantioselectivity. So that means one can get an enantioselective catalyst like this. Then another example which I said I will be talking about is the epoxide hydrolysis one. The structure of epoxide hydrolysis is something like this. If you can see, there's a 2 tyrosine units, which are then, this is the catalytic site, and the triad is here. So this is aspartic acid, histidine triad, and there's also a serine residue involved here. So this is an aspergillus epoxide hydrolysis. So, and these epoxide hydrolyses are found everywhere. The natural role of these are to detoxify the xenobiotics which the higher organism take up, and bacterial degradation of several environmental pollutants. So this is also involved in that. So these are some of the examples how epoxide hydrolase, once this is oxidized, it's converted into diols, and these diols are become more soluble, and so they can be excreted out. But examples of xenobiotics and contaminants hydrolyzed by epoxide hydrolase are some of these examples that is before. These are in the mammalian cells that they are. But where we really want to take this idea to. So the mechanism of epoxide hydrolase involves the activation of the epoxide ring by this tyrosine, and then this aspartic acid unit or aspartate then comes in and opens up, helps in opening up the epoxide ring. And then later on, the water, which is then activated with the histidine unit, it moves on, and it leads to the formation of this diol. Okay, so this is the mechanism. Now, can we use this mechanism of epoxide hydrolase to construct new catalyst? Well, this idea was taken up. By Hein quite early in 1985, and he came up with this sort of the tyrosine unit, and he developed this catalyst. And this simple looking catalyst was used for this transformation and ring opening of the epoxide with an amine, and they could get it in quite good yields. The product was obtained in quite good yields, and it's quite early that he came up with this idea. So giving you this background, I would like to take on to you to the type of work that we have done. So bio-inspired transformations, well, basically bio-inspired catalysts we have developed, and then we have moved on to and then extended that idea to include many other type of reactions in the process. So I'll be taking up these projects, but in addition to these simple projects, I've also added more to this, feeling that maybe we'll be needing more time. We'll be having more time, but I feel I can just move on with this. So to talk about this, this was our first mimicry of the epoxide hydrolase. We thought of using the same idea, but instead of that, we used a thiourea catalyst for epoxide ring opening, and we were quite successful. And it was showing regioselective ring opening that we could get it. Okay, so this was a racemic one. Then we were getting quite good yields, and although the regioselective ring opening was not very like it was favoring one of the regioisomer, but with the different amines we were getting these, and the yields were quite good. So nothing about that. So we studied a variety of these epoxides with different substituents, and we were able to see that how this functions. So in order to develop an enantioselective version of this reaction, we designed a peptide-based organocatalyst. And our idea was simply based upon this. If you just have a look at this, so our idea was that the epoxide should be activated by a thiourea unit, and there should be a holding unit for a nucleophile. And how can we use this? And there should be a turn, because the nucleophile should come near to the epoxide, which is holded by the thiourea. So we came across this, and we came across that if one can use a beta turn that can actually do what we were expecting it to do. So this beta turn could be introduced with the help of sequential L-proline and D-proline, and in small peptides it can be introduced as this other beta turn is introduced by D-proline and glycine amino acid sequence. But we developed this process, and we developed a number of these tripeptides, which were on one side, the N-terminal end was having the thiourea, the C-terminal end was having it as an ester. We also developed what you call one of these amides also here in place of esters, but more work was done with esters and different. And another, we kept on replacing the N-terminal amino acid, and we try to see which gives us a better result. So first idea was to synthesize these molecules, these tripeptide thiourea units, and a variety of these were synthesized, and then wearing this C-terminal end also, different esters were introduced other than the normal ones. And we also worked with CS2H here also to see which actually gives us a better result. Okay, so we also developed a tetrapeptide also, but most of this work was done with tripeptide. Now, what did we see when we tried to use these as catalyst for the type of transformation we wanted to look for? So we were able to get success with the mesostilbene oxides. And they, when catalyzed by these tripeptidyl thiourea derivatives, gave us the product, which was an optically active one, but the enantioselectivity was, we couldn't achieve much enantioselectivity greater than 79%. But anyway, we were able to, whatsoever we hypothesized earlier, we were able to actually execute it. And we were like happy to receive even these results, and which we thought can be further modified to get this. So if you look at this, these are some catalyst screening that we did, and the best enantioselectivity was initially 35%, which was then further improved by varying different conditions, optimization of the reaction conditions, and we were able to get these enantiomeric excess. So what the maximum we were getting with L-phenylalanine, L-proline, D-proline, OME, that is the C-terminal is an ester, methyl ester, 79% yield. This when we had D-proline, D-phenylalanine, D-proline, and L-proline, it was 82% and 76% in enantiomeric excess. That is what we got. Okay. So varying these differently, and these are all L-pro tripeptide amino acid residues. These are all D. What you find is that they are less. So actually, L-pro, D-pro, L-pro provides that beta turn that we wanted it to have, and also it also is responsible for the providing the chiral environment for this reaction to give us products which were selective. So we proposed a transition state, probably looks like this, and that is what leads to this product. And the stereogenic centers absolute configuration was then determined by running an X-ray analysis of the product. So we were like successful to support our hypothesis to some extent, although we couldn't get in the very first instance this high enantiomeric excess, but the enantiomeric excess could be improved by simply carrying out one level of recrystallization, and that improved to around 95%. So this is what is reported. Then if we talk about, this was highlighted on Asian Journal of front cover of Asian Journal of Chemistry, Organic Chemistry. And then let me take you on to bioinspired decarboxylated carbon-carbon bond formation reaction that we developed a catalyst which was like decarboxylation reactions, and we tried to look at some of these examples. So since this has been shown that cinchona-thioureas can be used for decarboxylative addition reactions, so we worked with these and we developed different thiourea derivatives, and we were able to get some enantioselectivity with these thiourea derivatives, and then we moved on to the squaramide-based catalyst, and we found slightly higher. Now, the initial results were just very less, 33% and 32%, as you can see. But further optimization of this actually helped us to improve the enantiomer excess, and simply moving to 1,4-dioxane, we were able to. So ethereal solvents actually helped us to get better enantiomeric excess in these cases. And this was an interesting molecule as well, certain amine that was. So we were able to get variety of substrate scope was then tried, and we were like it was quite uniform. You can see most of them are giving 90%, but EE. But when we come to this, it is 41% EE. So having this decarboxylative reactions, when we are using an aliphatic unit, then the enantiomeric excess is comparatively lower. When we are using a phenyl here, the enantiomeric excess is comparatively higher. Okay. So these were another substrate scope, extension of the substrate scope, just to include some heterocyclic units also, and some different derivatives of these substituents on the phenyl ring as well. So then we tried a single pot reaction for this, and which was successful, although the enantiomeric excess was slightly lower in this case than what we were getting earlier. So this is a single pot reaction. We carried out azavitic and then decarboxylative managed reaction leading to the formation of. So these were the 5 substrates that we could, products that we could make out, synthesize with this, just to show that one can do this single pot reaction as well. So we need to propose a transition state, and transition state can be proposed only after getting the X-ray crystal structure, because we are not aware what is the stereogenic center at the, what is the absolute configuration of the stereogenic center. So once we have this X-ray structure, we were able to propose that there's a rephase attack leading to an S-configured stereogenic center, and this was disfavored, and we could say that this is because of the steric reason that the other enantiomer was being disfavored to a greater extent. So this project actually highlighted the importance of using this cinchona alkaloids, which have bifunctional catalytic catalysts, which and we were able to propose a mechanism of synergic activation, which was demonstrated by the results that we obtained. Then moving on with the similar concept, I'll just introduce, we just changed the molecule, and we were able to get a very good results in this case as well. And again, we were able, we could see that the squaramide catalyst came out to be the best catalyst in catalyst screening again. But here, instead of dioxane, it is CPME, which was giving us better results. So we moved on, and the substrate scope was tried, and we again was getting quite good for in this case, since there are two stereogenic centers, we were getting diastereomers, and although the diasteromeric ratio was not very good, but as far as the enantiomeric excess of both the diastereomers was concerned, it was quite high. Okay. So these are the substrate scope looking at different, and more or less they were uniform, excepting some examples where we were getting slightly lesser enantiomeric excess. So just like in the previous cases, we tried to propose a transition state here as well, and which goes along with this, but we were not able to make a crystal for this, so we are not sure what is the stereogenic center at this very point. Then taking on to extending our work with the Cinchona thiourea catalyst to other reactions. So we worked with the sissamol derivative and this isatin, and we were successful. And now sissamols are considered to be nucleophilic, but not very high nucleophile. They're not very strong nucleophiles. But under these milder conditions, we were able to get the products. And in initial screening of the solvent, after the screening of the catalyst, we were again found that it's the ether solvent which was giving good results, quite selective. So we just worked on this. So optimized conditions is shown here. So it was 10 mole % of the catalyst that we were using, synconidine thiourea catalyst in this case. So, and then the substrate scope was evaluated. And when we evaluated the substrate scope, more or less it was within the range, but some of them, well, sissamol was one constant thing that we were working on, but then we tried to change the substituent at the 5 position of the isatin derivative. This was the one which gave us the highest enantiomeric excess, while most of them was 88, 90 and all that, and 86, as you can see in these cases. So this was an interesting point because sissamol is showing reactivity under very, very mild conditions. Well, we were able to get the crystal structure for this done, and our stereogenic center was then defined, and then we tried to build up the transition state model to say why R, why not S, and so it was quite depictive, and we could say that why R is favorably formed. So this methodology is a very simple, environmentally benign, and it is delivering quite enantioselective products. Then Cinchona thiourea organocatalyst was found to be catalyst of choice than other modified Cinchona alkaloids. So the next project, I'll take you on to Filkoff reaction of phenol derivatives with isatin, which is an enantioselective. Again, now here I'm just now we were talking about sissamol. Here I'll take you quickly because it's more like this similar reaction and the similar catalyst also, which was found to be active. But again, this has slightly less reactivity than sissamol itself. So this was found to be giving us this moderate, not very high yields, but we can call them moderate. Here again, THF, which is a ethereal solvent, which was found to be giving during optimization better results, although not reaching 99% enantioselectivity, but the maximum that we could get in this case was 78%. So it was mostly in the range of 70s, but we could see that in some cases it was even less. Now the reactivity is also less, and so probably it doesn't fit in properly. But this is one example when we had more substituents on it, like OME. When we worked with phenols, different phenols, moved from naphthol to phenols, then this was giving at 92% enantioselectivity. So we ran a single crystal X-ray, and here again we got what was the R-configured stereogenic center. And so we propose that this is how probably it is activated by the thiourea catalyst, and this nitrogen actually activates the phenolic unit, just like in sesamol. Okay. So to conclude this portion, we can say the Spindletop reaction of less explored arenes, dimethoxyphenols, and naphthols with a certain derivatives under mild conditions, we were successful in developing them, and products were isolated in good yields and ensure selectivities to an extent. Then this is quite an interesting work which I would like to share with you. Morica-Baylis element reaction of melamide with this certain. Melamide undergoes reactions like these. So they've emerged as very good dinophiles, dipolarophiles, and asymmetric cycloadhesions, as well as Michael acceptors in stereoselective. So nucleophile can add on to this, or a cycloadhesion reaction, or this type of dipolarophile cycloadhesion reactions have occurred, or this reaction where nucleophile adds on one carbon and the electrophile adds on to the another carbon. So these are the common reactions which are listed in literature for this melamide. We came across this reaction, which was published from Dr. Perumal's lab at Center Research Institute for Leather Technology in 2010, and he has shown that DAPCO, in the presence of DAPCO, this cysteine undergoes reaction with melamide, and this is, if you see, is not a nucleophilic addition. Here, actually, the melamide is acting as a nucleophile, so it's a Baylis element type of reaction which is occurring, and he has proposed this mechanism for this reaction, that the DAPCO actually activates this as a Baylis element donor, and this cysteine acts as a Baylis element acceptor, and this gives the results. We try to see if we can transform this concept into an for producing optically active molecules. So we have worked with this cysteine and cysteine in the form of carbon-oxygen double bond and carbon-nitrogen double bond. And, we have been successful in getting these reactions. So the first one was this. And the catalyst here, we screened all the catalysts, but we found that beta-isocupridine is the catalyst of choice for this reaction. And you can see the yields were very, very good. Sorry, yields are not that good, but enantiomer selectivity is very good for this. But thiourea was not very successful. Simple cinchona alkaloids were also not very good. And this was not even giving any reaction. So that means blocking this can have an issue with this. So let's see. So once we came up with this beta-isocupridine and realized that this gives us a reaction, then we went for solvent optimization. And interestingly, in this, we found that chloroform was giving us better results. But if you see, there's not much difference as far as the other solvents are also concerned. But the only reason that we got 99%, greater than 99% in chloroform, so we worked with chloroform. We could have worked with DCM also, or for that matter, toluene also. So the solvent is not making much difference. As far as ACN is concerned, yes, or methanol is concerned, there's a lot of difference as far as this is concerned. Okay. I just moved faster. Let me just see. Okay. So then we went for the substrate scope, and we were like happy to see that most of these could be giving us the product. But interesting was that we could use a melamide as a nucleophilic unit in this reaction. So again, based upon we came up with that there is an R configuration at the center, and we proposed these transition state for this reaction, and he said showed why probably this S is not giving us the results. Okay, So moving on, well, anyway, it's important to share with you that we got this cover for this also, inside cover in the Asian Journal of Organic Chemistry for this work as well. So extended the same concept to isatinamine. We were again successful in this. I'll just quickly go through this because the concept is the same and the catalysts more or less are the same. And again, the catalyst is more or less the same, but the natural selectivity of the products is not as high as we achieved in case of isatin. So isatinamine results in slightly lower natural selectivity of the products. And if you go by this, again, the stereogenic center were having the same. We propose it's more or less the same based upon our earlier experience. And we were also given a front cover in organic and biomolecular chemistry for this transformation. So that is interesting. And so concluding this portion, we can say this asymmetric Morita-Bellis-Hillman and Asa-Morita-Bellis-Hillman reactions, they have been studied by us, and we have found that beta-isocupridine catalysts are the ones which are actually modified cinchona alkaloids have been found to be the best catalyst for this type of transformation. So, okay, we are, just giving you an extension. Well, my title says carbon-carbon formation. Then I thought, why not to share one more reaction? But here it is carbon-phosphorus bond formation using similar catalysts. So it's the same idea. So we were able to get this alpha aminophosphonates. So it's hydrophosphonylation of ketimines, and which gave us the results in a quite comparatively good yields. So substrate scope, if you see, we're getting 97% enantiomeric excess in this case, and so thiourea catalyst is the best that we could find. And quickly, I'll just show you well how it happens. So if we have this, then in one case there were no reaction when ethyl was used, but when we have the benzylic units, then we were getting the reaction. This was interesting to see. Diethyl phosphites didn't give us the reaction, and this may be due to the low reactivity of these units, moieties, and the reaction of dibenzyl phosphite with isatinamine provided adductive good yields, but with low enantiomer selectivity. So then we tried to develop a one-pot sequential reaction for this also, and we were successful in that, and we tried these 4 reactions, and although the enantiomer selectivities were, as seen earlier, was slightly less than what we obtained in the earlier case. So we did propose this, that this is how probably the transition state, favorable transition state looks like. So rephase attack occurs in this case, and the C-phase attack is disfavored. And so highly efficient organocatalytic approach for natural selective addition to diphenyl phosphine ketamine derivative for isatin using synchronidine thiourea was developed, and we were really happy. Well, this is carbon phosphorus bond formation reaction, which I've shared with you. So, well, I've come to the end of my lecture. This picture shows us, well, this was my group at different times. These were the contributors, and now they are all working independent assistant professors, most of them, and some of them are working in industry. And all of them are employed, excepting one with this lady. She is still in lab, and she'll be finishing her thesis soon. And at the end, I acknowledge the funding from CSR and then Department of Science and Technology through Science and Engineering Research Board and UGC, because I've been supported by these organizations with funds to do my research. And I thank my students who work with me, and actually it is their hands which produced this work. I was just there supervising their work and trying to arrange things for them, chemicals, funds, and everything. Okay, And thank you very much for your attention. I think I finished in time.
Thank you so much, sir. Yes, thank you so much for your very informative and valuable lecture. I think you achieved almost, in all cases, you achieved almost over 99% enantiomeric access. This is a very challenging task. Thank you so much. I personally tried this cystatine with indole, and we got 3 hydroxy substituted product, but definitely it's a racemic mixture with mandelic acid. So we will definitely try to design some I got some idea to design some biocatalyst or some asymmetric catalyst to improve the enantiomeric access. Thank you so much, sir. Now I'm requesting Chittaranjan Sinha, sir, Secretary, Indian Chemical Society. Please say a few words about sir's lecture. Sinha, sir, can you please unmute?
Yes.
Yes, sir. Please start your video. Yeah, thank you so much, sir.
Yes, sir. Yes, sir. Thank you, Professor Swapandeep Singh, for your nice presentation, particularly towards the sustainable development and use of atom economy in the chemical reactions, since the chemical compounds are so useful. And they were working for the long time on the field of indoles and its derivatives, cystatines and its derivatives, and also many other molecule using catalyst and biocatalyst. And in this presentation, I think our audience, particularly the young workers, should be benefited towards the achievement of the great success, since the enantiomeric access and the asymmetric synthesis, etc., they are very useful for the synthesis of pharmaceuticals as well as other molecules. And I think there are some people raise their hands for any queries.
Yes, sir. Nidja Saha, you please unmute and start your video and ask your question.
Yes.
Nidja, please unmute.
Hello, good morning, sir.
Yeah, good morning. Yeah, welcome.
It is a very nice lecture. So I want to know the one fact, that is, as you have used this cinchona alkaloids in your lecture, so how this that will be also present in the reaction mixer. So during the purification of compound, how you have isolated that from the reaction mixture? Is it through the column chromatography or?
Yeah. It is through column chromatography only. It is through column chromatography.
Okay.
You have to run that. You have to purify the compounds through column chromatography.
Okay.
Yeah.
Thank you, Nidja. Another person, Chetna ma'am. Can you please start your video?
Good morning, sir. I'm so sorry. There's an internet issue over here, so I'm unable to start my video. I will be out if I start my video. So extremely sorry about that. My question to sir is, Akal Sirji.
Sashikalji, you're welcome.
Sir, you had, in one of your slides, that is slide number 14, you spoke about your thiourea and urea as the catalyst that you have used.
Okay.
So my question is, apart from thiourea and urea, is it only the nitrogen-based compounds that we can use as the catalyst, or is there any other alternative source for it?
Well, if you have seen this, nitrogen actually is the base that we need for making the anion in the process.
Okay, sir.
Okay, so nitrogen is required, and this cinchona alkaloids actually function as what we call bifunctional catalyst.
Okay,
so
sir.
these bifunctional catalysts actually are really useful in this. And if you see this slide 14, which you have mentioned,
yes,
actually they have devised a trifunctional catalyst, which acts as a journal. There's a nitrogen, pyridine nitrogen, which acts as a journal base.
Right,
and
sir.
There is an OH, the oxygen, the alcoholic unit, which acts as a nucleophile.
Yes.
And then there is an oxyanion hole, where through hydrogen bonding it activates the substrate.
Yes,
so this is all these components are required in this organocatalyst, because You don't have usual Lewis acids, which we have
Okay.
when we use metal catalyst.
Okay.
So we don't use metal catalyst at all in this. So
Okay,
some source has to be there.
Okay.
Okay. So that is how it has to be.
Yeah. Thank you so much, sir.
You're welcome.
Thank you, ma'am. Now I'm requesting Devlina, madam, you raise your hand. Please start your video. And
yes, sir. Very good afternoon
Good
to you
afternoon.
and all the participants. Actually, that was a very enlightening lecture, and of course, it gave a lot of set of information to us.
Thank you.
Apart from that, I have a query that the intermediate that has been like proposed through the interactions with the substrate and the catalyst, on the basis of which the site was detected in the mechanism, was it trapped with any kind of experimental study during the experimental study?
Not in every project, but in earlier projects, we have tried to see what is the role of the different units of the catalyst. And we could make out if we block one of the units, like just now I've been asked about the nitrogen. So if we block nitrogen, the reaction doesn't occur. Or if there's a thiourea unit in place of NH, we have N-methyl, even then the reaction doesn't occur. Or if it occurs, then enantiomer selectivity is not there. So these are the issues that we did try to look at.
Okay.
Since we were like confident in our initial work, we did everything. We just worked around everything. And then, well, these were like staple sort of catalysts which could be used on the shelf. Any one of you can use them for your transformations if you want.
Yes.
And there's a lot of work on that. Yeah, even sometimes these are modified Syncona catalyst. We're making it thiourea or a pyramide catalyst, or even beta isocupridine. But in some of our examples, we have even found that simple Syncona alkaloids, you don't have to modify anything. They have also been found to give us very good results in certain reactions, and more than 90% enantiomer selectivities have been obtained with them as well.
Okay, that's the kind of indirect way to detect, I think.
Yeah,
because
that's all.
Because I have seen in some of the papers they have used mass for detecting the intermediate.
In one or two of our papers, we have also done that. We have also done that. But that is only an additional evidence that we try to give how it must be working. Yes. So what interaction between the catalyst and the substrate is there, and are there all the two substrates that we are using? They are with the catalyst, or they are not. But sometimes that is quite tricky, you know. You cannot be sure of what you're saying, or the only thing is that if it works out to be the same mass that you want to predict, then yes, you can do. But still, you cannot be very sure. But when you run those reactions with the blocked or catalyst or modified catalyst, which are having only one functionality, which is active, then that is the true evidence that you get. Right.
Yeah. It's a matter of chance to get the mass correctly, I suppose.
I mean, we have done some, and we have reported in one or two of our papers also. And recently, we got one of our paper accepted. In fact, the reviewer got it removed from the manuscript. He said, no, this is not viable.
Okay, fine. And the other question is the molecules, I think, are very novel, the products which have been developed. So are they like for further processing towards the biological activity? Means are you planning for it, or solid?
No. Well, in my lab, we just focus on one thing. We don't get into others. If somebody is interested, we can provide the
for collaborative work or so.
That is feasible, because we just focus on developing reactions where we can get enantiomer selective products. So just that.
Okay, that's nice piece of information. Thank you so much.
Thank you, Devlina ma'am. Thank you, Professor Chimni. Thank you so much for your valuable time. I think our participants learned many things about asymmetric synthesis. Now, our next speaker, 8th speaker, Professor R.K. Sharma sir, have also joined with us. So thank you so much again, Swapandeep sir. Now,
let me thank on behalf of Indian Chemical Society to Professor Singh. Also I do request to Professor Singh for submitting this original research to any one of your research to the Journals of Indian Chemical Society.
Yeah, sure.
That is now publishing by Elsevier.
Okay, okay.
So
That's
thank
great.
you, Professor Singh.
Yeah, thank you very much,
Thank
sir.
you, sir.
My pleasure.
Thank you,
My
sir.
pleasure.
Now I'm requesting Professor R.K. Sharma, sir. Sir, can you please hear? Can you hear me? Yes, sir. Your mic is muted, sir. Can you please unmute your mic? Sir, your mic is still muted. We have made you the co-host, but your mic is still muted, sir. You can rejoin, sir.
Yeah.
Now it is okay. Now
Because coming host is not allowing to unmute.
Okay, sir. Sorry for this technical error. So thank you so much, sir. Thank you so much for giving us this your valuable time, and this is a good opportunity for all our participants. So it is already 10 minutes, 11:10. So I think we can utilize this time after 12 because there is no lecture after 12. So you can take extra time also. So dear participants, let me introduce Sir Professor R.K. Sharma, sir. Sir is this this is the 8th scientific lecture, and Sir will deliver his lecture on Green Chemistry Network Center, accelerating innovation through research and educational initiatives in green chemistry. Professor R.K. Sharma, sir, is a coordinator, Green Chemistry Network Center, and professor of Department of Chemistry, University of Delhi. Let me say a few words about Professor Sharma. Professor R.K. Sharma sir is my direct teacher. He taught us group theory during my MSc, and I still remember those days. Without any documents or materials or any books, he taught throughout the semester the group theory. I'm very happy to listen to you, sir, again. Now, Professor R.K. Sharma sir is a professor of Department of Chemistry, as I said. He received many prestigious awards. He produced 36 PhD, supervised 36 PhD students, and published more than 150 research articles. He is the fellow of Royal Society of Chemistry and received so many research publications. One recently published article, he has published one research article in Chemical Society Reviews, Ipec 54. So all his research work he has published in so in highly cited journals. I am very much thankful to Sir that Sir has allowed me to collaborate with him, and we are jointly editing one book. I have already shared the information of this book in the group. So with this small introduction, I'm again welcoming you, sir. Thank you so much. You have already shared your slide. Please make it the full screen and please start your presentation. Thank you, sir. Over to you, sir.
Okay. So thank you, Dr. Babun, for inviting me to deliver the lecture. And as you can see, I'm from Department of Chemistry, University of Delhi. And we have a Green Chemistry Network Center established in Delhi University under the recommendation of a panel of world leaders headed by Professor Paul Anastas. And this man is known as father of green chemistry. This network center is actually working for building a green chemistry network all over India, preparing and disseminating green chemistry educational material, designing training workshops, and taking up green chemistry research projects. We have research projects from CSIR, UGC, DST, DBT, industry. Even recently, we got a major project from Ministry of Textile for setting up a Green Chemistry Network Center laboratory. So in my talk today, I'm going to share with you briefly share with you about these activities also. But before going to green chemistry, let us see the importance of green chemistry. You know, this came in Chemical and Engineering News that sustainable chemistry legislation enacted by US Congress. And this US Congress enacted a law which will promote green chemistry concepts in federal grants. So this shows the importance of green chemistry in research and education. But before going to green chemistry, let us see what chemistry is giving us. You know that this is the chemistry which is not only extending the length of the life, which was 47 years in 1900 to 75 years, but also increasing quality of life by providing so many things. So actually, we chemists are making world worth living, but there is another side of chemistry. Chemistry also leads to toxic world. Chemistry also leads to waste disposal, pollution, accidents, landfill, danger, depletion of natural resources. And according to the survey done by this Nobel Prize winner, Richard Smalley, according to him, humanity's top problems for the next 50 years are energy, water, environment, and food. You know, he said the more serious problem is population growth, and mostly in developing countries. So he said there were the 7 billion people in 2011 and expected to be 9+ billion people by 2050. And this is a very serious problem in countries like India. A very interesting comparison if you see about the population growth. In India, a population of just one state, Rajasthan, is equal to the population of whole UK. Same way, population of UP is equal to population of Brazil. Population of France is equal to population of Madhya Pradesh. So much problem of population growth in India. And we know already that nature provides us resources. We are consuming these resources and then creating waste. And again, nature converts this waste to resources, and this way the cycle goes on. But because of the population growth, we are exceeding the carrying capacity of the earth. We are using resources and creating waste faster. The earth can take our waste and convert them back into the resources. So now we are consuming natural capital rather than just the interest. So now this is one way, this arrow, resources to waste. So the question arises whether green chemistry can help in reversing this arrow, waste to wealth or waste to resources. Let us see that also. You know, this looks like a graphic art, but it's not. This is an example of waste. Just you see more closer look, a more closer look. You know, 2 million plastic bottles discarded every 5 seconds in the US, and 86% of plastic bottles used in US end up in landfills, taking up 1,000 years to biodegrade. This is the report by ACS, and you can see this here, that there is only generation of plastics, no recovery at all. And because of that, there is plastic contamination. 90% of floating debris in oceans is plastic, projected to grow tenfold in 10 years. Plastic found in 48 to 86% seawards in mammals. And more serious problem associated with this is plastic bottles. The plastic bottles which we are using, they are containing bisphenol A chemical, which after contact with hot liquid, this releases. And according to the recent research, this BPA linked to breast cancer in women, brain damage in children, obesity, heart disease, etc. And even then we are using the same plastic bottles for drinking water. Another graphic art, if you can see this or guess what is this. This is again an example of waste. More closer look. A more closer look. You know, 4,26,000 cell phones retired each day in the US. And India is the second largest mobile phone market in the world after China. And this e-waste, what US is doing in terms of recycling of e-waste, between 50 to 80% of the e-waste collected for recycling are not recycled, but is very quickly placed on container ships bound for destination like China. You can see this, and this is not a solution. You know, according to the US Department of Toxic Substances Control, determined that the most electronic devices are toxic based on 1,000 different substances in e-waste. You can see the list: lead, tin, copper, antimony, cadmium, mercury, chromium. Plastic includes PVC, chlorinated, phosphorus-based flame retardant, so many like, and all of which can be poisonous to people and wildlife. And we are not careful about these e-waste. And according to this report in a newspaper, Times of India, Delhi is the second largest producer of e-waste in the country after Mumbai. You know, 2-3 times I was invited for the live show in Doordarshan, and we discussed about this problem, about impact of waste on environment and if there's a role for green chemistry. We have discussed in a live show. So a big question before us is, within the next 50 years, how can we provide 8 to 10 billion people with energy, water, food, quality of life and future technology, and that is without global warming, without resource depletion, and without toxics in environment. And the one answer from my side is green chemistry. So I'm going to elaborate this also in my talk. But before that, the question arises, what is this green chemistry? And why we are talking now about green chemistry? So I'm going to answer this question first, what is this green chemistry? Just by taking one slide, I'm going to define that green chemistry, one slide, one relation. You know, risk is a function of hazard and exposure. If you want to minimize risk, either you minimize hazard or you minimize exposure. And the traditional way of minimizing risk is by minimizing exposure, putting gloves or safety glasses or helmet, or lab coat. This is the traditional way. But if you can minimize this hazard, either reduce or eliminate this hazard, you can minimize the risk even if there is any accidental exposure. Sorry. And the green chemistry is based on this. Sorry. So what is green chemistry? Green chemistry is the design of chemical products and processes that reduce or eliminate the use and the generation of hazardous substances. Slowly, people started recognizing the benefit of green chemistry. And finally, in 2005, Nobel Prize went to green chemists. And you just see the words of Nobel Committee. According to that, this is a great step forward for green chemistry, applying basic science to the problem of man, society, and the environment. So this proves that the best chemists in the world are doing green chemistry. There are two founders of green chemistry. One is Professor Paul Anastas, another is Professor John Warner. And both of them written a book, which is very good book for beginners. And this book is Green Chemistry, Theory and Practice, published by Oxford Press. And this book is already translated into several languages. And in this book, they had written 12 principles of green chemistry. And these 12 principles are actually 12 tenets of green chemistry. These principles, they provide a framework for design of new material, products, and process. And systematic integration of these principles is key to achieving genuine sustainability for the simultaneous benefit of environment, economy, and society. These are the 12 principles of green chemistry. But I'm not going to touch these 12 green chemistry principles or 12 principles of green chemistry, because explaining these 12 principles will take at least one semester. Now, the biggest challenge of green chemistry is to get people to adopt it, to convince people to do green chemistry. So what we did, we started way back from 1999, this mission, popularize green chemistry. In 1999, we had organized a national symposium on green chemistry. Then in 2001, the Ipec International Symposium on Green Chemistry was organized. That was proved to be excellent event. You can see here, there's a James Clark, even Sheila Dikshit, that time she was the Chief Minister of Delhi. She came for the inaugural session. But we found that the people were reluctant to change. They were taking green chemistry very lightly. They used to question us that if there is green chemistry, then there should be red chemistry, yellow chemistry, pink chemistry. But we know that change always comes very slowly than anyone would expect. There are always impediments to innovation. And simply stated, people don't like to do things differently from the way they have done them before. They don't want to come out of their comfort zone. And new ideas and new perspectives often face harsh opposition. And there are very interesting examples to support this. Manleaf, inventor of periodic table, refused to acknowledge the existence of radiation or even the electron. The great Einstein rejected quantum mechanics. He said, quantum theory is certainly imposing, but an inner voice tells me that it is not yet the real thing. And the finally this Daniel, this is a very interesting case with him, who got the Nobel Prize by discovering the existence of this type of crystals, quasi-crystals. And he won the Nobel Prize in 2011. He said when he discovered that, people just laughed at me. And even head of his research group, after telling Daniel's book, the head of his research group asked him to leave for bringing disgrace on the team, and I felt rejected. You do a new thing, and we know the benefits of green chemistry. So we continued to work for the popularization of green chemistry. And these words of Mahatma Gandhi encouraged us to in this popularization mission. I think there's some problem with network. So Mahatma Gandhi said that the first they ignore you, then they laugh at you, then they fight you, and then you win. So these words of Mahatma Gandhi encouraged us for this popularization mission. And we found that if we want to incorporate green chemistry principles in academia or in industry, the best way is organizing conferences. So what we did, we had organized a workshop, Indo-US Science and Technology Forum supported workshop. This was the workshop. And you can see the inaugural session. This is a picture of inaugural session. And DST secretary at that time inaugurated this inaugural session. And you just see this man gave the inaugural lecture, delivered the inaugural lecture. And this man is known as Paul Anastas, father of green chemistry. So father of green chemistry, Paul Anastas, came to India. That time he was the advisor, scientific advisor to US president. And he came and delivered the inaugural lecture in that workshop. All the world leaders, green chemistry world leaders, participated in this workshop. You can see Terry Collins, famous for catalysis work, got the US Presidential Green Chemistry Challenge Award. This is Mary Kirchhoff. Dr. Mary Kirchhoff is now Director, Green Chemistry Institute of ACS. This is Robin Rogers, famous for ionic liquid work. And he also got the US Presidential Award. And these two are John Warner and Paul Anastas. These two are founders of green. So these world leaders of green chemistry, they recommended that if green chemistry is to grow in India, then there should be a green chemistry networking. So we started working on green chemistry networking. And we got Ipec Cameron GCI Den Grant Award continuously for 3 years for doing this networking. So we worked on networking. This is the simple form for joining the Green Chemistry Network. There's no fee, nothing is there. You just have to fill up and show your interest, and you can join us. We are every year organizing workshops like this is a symposium organized by Delhi and Gurgaon schools. These are the workshops every year we are organizing for green chemistry for the students, educators, and industries. You can see every year, this is in 2015, where DSC secretary, even these are the participants of the workshops, and you can see even DSC secretary participated, Ashutosh Sharma, in that workshop. Not only in Delhi, we are touching all parts of the country. We are conducting and participating in green chemistry workshops that were held in many parts of the country. And there's few examples: Nagpur, Niri, Assam, Punjab, Naipur, Hyderabad, Gujarat, then Rajasthan, Gujarat, Sikkim, Uttar Pradesh, Mizoram, then MMH College, Ghaziabad. This is in Central University, Garhwal, and all the media covered about this workshop on green chemistry. Even this is in Bihar. It was the teachers' meet organized by Association of Chemistry Teachers, Mumbai. So this is in Himachal Pradesh, Punjab, Udaipur, Rajasthan, Kerala, Jaipur, again in Jaipur. Then this is in Jalandhar. This is in Punjab University, Chandigarh. Now the question arises that what is the result of all this? We are delivering the lecture on popularization of green chemistry, about the benefits of green chemistry, but what is the result of it? So I'm just showing a case, a real world case, result of all these activities. So a real world case of green chemistry in Indian pharmaceutical industry, where wealth came from waste through green chemistry. So I'm going to take this case. You know, the green chemistry is about reducing waste, reducing materials, reducing hazard, reducing risk, reducing energy, reducing environmental impact, and overall reducing cost. And everything is followed in this real world case. So what was that case? I think all of you know about the ranitidine HCl drug. This is an important and cheapest anti-ulcer drug available to common man. And SMS Pharmaceutical is the world's largest manufacturer of this drug. Other manufacturer you can see here. Dr. Reddy's lab, Saraka. So what happened that the two companies, SMS Pharmaceutical and Saraka, were asked by Pollution Control Board to stop the plant, shut the factory due to the methyl mercaptan gas emission as waste from manufacturing process. So let us see what was the manufacturing process. You see here, these are the raw material, DMSO raw material, and then the production of ranitidine followed by methyl mercaptan. And this methyl mercaptan is very toxic. Even you can see the toxic effect of this methyl mercaptan. And this is gas is very horrendous smelling gas. Even you can smell this gas at even 1.6 ppb level. And this is having extremely disagreeable odor of rotten cabbage. So, and the traditional practice was ineffective. You can see so much input, methane, diesel, water, and even then there is the output, solid waste, unscrubbed flue gases, and even then there is release of methyl mercaptan. So because of that, the Pollution Control Board instructed these two industries that you shut your plant. So what happened, then green chemistry came into the play. A green chemist who was working with us, helping us in popularizing green chemistry, and that time he was the dean head at IIT Guwahati. He designed a catalyst. Now he was vice chancellor of Tejpur Central University, 2 terms, and now he is higher education advisor of Assam government. So he designed a catalyst for this industry, and that catalyst did the wonder. What was the toxic gas? Methyl mercaptan. That catalyst converted that gas to DMSO. And DMSO, you know, they were using as raw material. This was the raw material. So this was again used in ranitidine production as raw material. And because of that, because what was the waste toxic gas converted to raw material, because of that, there was cost reduction, about 40% cost was reduced. So you can see the advantages: low capital cost, reduced cost of production, nominal supervision, highly protective, and environmental friendly. I got a mail from that industry, and they invited me to visit the plant. And in that letter, they had written that, being inspired by your speech in the conference on green chemistry held at IIT Guwahati, we have concentrated on one of the burning problems of Hyderabad Valkenda drug industry. So the same way as I'm delivering a popularization lecture here, the same way there was the conference at IIT Guwahati on green chemistry, and I was delivering the lecture on green chemistry there, and they were attending that conference, and they thought that green chemistry might help them, and green chemistry did help them. So as I said, they have invited me, so I visited their plant, and not only me, with me, there were 2 Pollution Control Board people. One is Additional Director, CPCB, this is Dr. DC Sharma. Another was the MD and Sima, his member secretary, Karnataka State Pollution Control Board. And they were so happy. There was no smell. Everything was clean, and they have explained everything. And they were so happy that they requested us that if you are organizing another workshop on green chemistry, please invite us also. So this was a very good case for us on real world case on green chemistry. So we have displayed this case on our website. And then we got a mail from Dr. Reddy's industry. So Dr. Reddy's lab, I got a mail from them that ours is a pharmaceutical industry manufacturing ranitidine. As per the website, there is a development on wealth from waste. Say methyl mercaptan gas is converted to DMSO. Can I know more details of this? So we have guided them, and they have also putting up plant in Hyderabad. You know already that these are the 12 principles of green chemistry. And one of the very important principles is use of selective catalyst. And catalyst is so important that according to this Nobel Prize winner, very sharpless, catalyst is the engine that drives the development of chemistry. And even, according to this report, catalysts are essential in the synthesis of even more than 90% of the chemical industry product. And one of the great things about catalysts is that even a slight improvement in their performance can be worth millions. So important to do research on this area. And this is again supported by the Nobel Prize winner in this field, catalysis field. 2005, then 2001, 73, 63, 1918, 1909, and then 2010, Nobel Prize in Chemistry awarded to palladium catalyzed organic synthesis. So this is very important area. And we are also working in this area. My group is also working in this area. What we are doing, we are combining the activity, and there are two types of catalysts, homogeneous and heterogeneous. So homogeneous catalysts are very active and selective, and heterogeneous catalysts are not so active and selective, but they are easy to separate and reuse. So what we are doing, we are combining the activity and selectivity of a homogeneous catalyst with the ease of separation and reuse. So with the ease of separation and reuse of a heterogeneous catalyst, we have reviewed our work and published in Green Chemistry Journal and even in Coordination Chemistry reviews. Even you see the last few years, 3 years, few publications published by my group. You can see these Dalton transaction, material horizons, inorganic chemistry, then ChemSysChem, ChemCatChem, RSC advances, then material chemistry frontiers, material horizons, general chemical education, ChemCom, ACS Omega, chemistry select, then Nature Scientific Report, and then chemistry select, then green chemistry, then ACS Omega, Chem plus Chem, green chemistry again, ACS Sustainable Chemistry and Engineering, New Journal of Chemistry, Journal of Material Sciences, even green chemistry, catalysis science and technology, Dalton transaction again, then Journal of Material Chemistry, green chemistry, Journal of Material Chemistry A, and Journal of Molecular Catalysis. And I'm very happy to share with you that, in our area, green chemistry, this is the top ranking journal, is Green Chemistry Journal, published by Royal Society of Chemistry. So we got a mail from the editor of that Green Chemistry Journal that I am emailing to let you know that your article was one of the most downloaded articles in green chemistry. So we are very happy that at least our research work is recognized worldwide. Not only this, even a research paper published by us in Nature Scientific Reports, I got a mail from the editor of that our article is in the top 100 scientific report, Nature Scientific Report chemistry papers. Even recently, we have published an article in Material Horizons, and that was the most popular article published in this Material Horizons. Even recently, because we are working on catalysis and nanocatalysts, so recently we have published a review in Chemical Society Reviews on silver nanomaterial and catalytic application. And we are happy to report this, that this is very popular Chemical Society Reviews journal having impact factor 54.56. Even considering the popularity of our work, World Scientific Press, they have invited me to write a book on our work, silica-based organic and inorganic hybrid nanomaterials. So we have written a book, and that was published by World Scientific Press. Wherever we are going, we are showing industry or academia just to compare the impact factors of different journals, and you will find the journal publishing green chemistry research are having higher impact factor. This also shows the importance of green chemistry. We are going to industries also. This is in Mumbai for industries. We had organized a workshop. Over 300 chemical industries participated in that. And even Polynestars, John Warner, that time the DSC secretary was Ramaswamy. He also came and participated. Even I was invited by Gujarat Industries and Pollution Control Board on green technologies in unit operations, and I was the opening speaker. And this came in media also, newspaper, even our Prime Minister also praised about this. You know, the Dr. Eddy's lab is the major industry, pharmaceutical industry. And every year they used to celebrate Science Day by organizing a Science Day Symposium. Because of the COVID, they had not organized last year. But in 2000, and in that symposium, they used to invite one speaker from all over India. So in 2019, I was invited in that to deliver the green chemistry lecture. This was JICE invited me in Japan for delivering green chemistry lecture. Even this is even one of the largest symposium on analytical chemistry. Every year, this was organized in New Jersey, Crown Plaza, Princeton Conference Center. And this time in 2019, this was, the theme was sustainable solutions. So I was invited to deliver lecture in this, and I have delivered the lecture on green chemistry and water treatment from vision to action. This is another work I just want to share with you, my research. You can see this periodic table, and in that these metals in red color, you can see this red color metals. These are going to exhaust. All the metals mostly which are used, they are like having the lifetime red 5 to 50 years and 50 to 100. So these metal reserves are exhausting. Even one can experience this in the form of the cost of these or the prices of these metals. Since 2000, the price of copper has quadrupled and price of platinum has tripled. Even the rare earth elements have collectively increased in price by a factor of 20. And mostly this rare earth metal reserve is in China. And indium prices, you can see, rose a staggering 800% in 6 years. This is the case for all bulk metals, precious metals, rare earths. So what we need recycling of these metal ions, because we are using these metal ions and throwing these metals in the environment. And this metal reserve is exhausted. So this was a news in Hindustan Times that because China is having rare earth reserves, so will China weaponize rare earth metal in trade war with the US? And this is very recently, this came in Chemical and Engineering News cover story. So because of that, because China is having rare earth reserves, so as a global demand for rare earth metal grows, the US Department of Energy is investing millions of dollars to secure potentially sustainable domestic source of these commercially critical elements from coal and coal waste. Even this is, they are spending a lot of money to recover these rare earths. So because of the depletion of resources at an alarming rate, what is highly desirable is recapture of these metal ions. There should be a technology developed for recovery of these metal ions. So what my research group did, we have developed a chelating polymer. You see a polymer, we had immobilized a multidentate, chelating it on this polymer. And this chelating ligand is very selective for a particular metal ion. So you can see we have developed that, and this is a bottle with chromium solution. I'm sorry. And you know, just when we have added this, sorry, chromium, this chelating resin, you can see the color is, all the chromium was absorbed. And we can again recover that pure chromium. So we have developed, we have even patented this technology. We have developed scavengers for chromium, even for iron. And also we have designed a small bioreactor for online recovery of these metal ions. So you can see that we have patented this also. And we got a major project from DST to fabricate a bigger bioreactor. Even I was invited, just to show you the response of public. I was invited by the Kanpur DAB College to deliver a lecture, a keynote. And you can see here, even the Kanpur University Vice Chancellor, another Vice Chancellor, and this came in all the media. And there was so response that even more than 5,000 people attended this lecture. And this came in all the media because of the chromium problem in Kanpur. Kanpur is having tannery industry, and tannery, they are using chromium, releasing chromium in water and land, and there's so much problem because of that. Even we had organized a SCS workshop on sustainability and water quality, supported by Global Innovation Imperative, GII. And in that, around 6 experts from US, water quality expert, participated, and we have demonstrated our technology developed for metal solution. Even these are the other reports for, like, we have developed the chelating polymer for palladium recovery, for molybdenum recovery. This is in Journal of Material Chemistry A for lead. We have published. We are writing chapters in different. This is RSC Green Chemistry series. Then this is another book. This is another. This is Green Chemistry to Solution. And now we are working on designing magnetic nanomaterial for extracting these metal ions. So we have designed that, and you can see how these magnetic nanomaterial are extracted using a magnet. This was the major project sanctioned by DST. So this is about the research. Now, in short, I will discuss with you about the educational activities. What type of educational activities we are doing. You know, we have incorporated green chemistry paper in undergraduate syllabi. 3 green chemistry papers of Delhi University. And even some of the colleges like Miranda House, which is in ranking or NIRF ranking is #1 in India. So they are also running add-on course on green chemistry, and we are helping them. Again, internet connection. This problem in internet connection, yeah. So this is one paper we have introduced as a general elective course in undergraduate syllabi of Delhi University. This can be taken up by any student of any like arts stream or other subject they can take, and this is just to inspire them that you should see the green chemistry is there and what way this can help. So just to inspire the student, this paper was even, you know, just to show you that the MS, this University, Central University of Rajasthan was the first university that started MSc in green chemistry. You can see there the specialization in green chemistry. And we have, I and Professor Ranu, we have designed the syllabus for green chemistry for them. Recently, we had written a book, introductory text on green chemistry for undergraduate students, and this was published by Bailey. This is just to recognize our work on green chemistry. We got an award, even NISA awarded us honorary fellow. This is just last week. This was published by Stanford publication, the green chemistry for beginners, and the foreword of this book is written by father of green chemistry, Paul Anastas. You know, the Journal of Chemical Education is the best journal if you want to see the topics or the experiments on green chemistry, and this is published by American Chemical Society. So what we are doing, we are developing experiments on green chemistry and publishing those experiments in Journal of Chemical Education. So you can see this experiment is published in this. Then another experiment, preparation of gold nanoparticle using tea, that was published in this. And we got a mail from editor of this Journal of Chemical Education that this is the most read experiment, green chemistry experiment. Even there is a green chemistry excellence center in the University of York, UK. They, in their newsletter, they have published that this experiment is a breakthrough, and nano T, you can see. We had written a monograph on green chemistry experiments, and this monograph written by Professor Paul Anastas, father of green chemistry. And this was released in a conference by the cabinet minister and Professor John Warner, who is founder of green chemistry. And the funding we have received from DST for designing and revalidation of green chemistry experiment. Dr. Bubun, how much time is left? Dr. Bubun? Can you tell me?
Yes, sir. Yes, sir. You can take 10 to 15 minutes, no problem, sir. Because our next speaker start 2 p.m. So you can take no problem. 10 to 15 minutes.
Okay. So what we are recommending to our students that before starting the experiments, they should know that what type of chemicals they are dealing with. Maybe that chemical may be a high-risk chemical or environmentally damaging chemical. So we are recommending that they should first go through the MSDS of that chemical. And this material safety data sheet is available freely on this website. And this is also recommended by ACS. www.msds.com. And you know, the major incentives on green chemistry experiments is safety, high safety, low cost, and high performance. And these are the major incentives of implementing green chemistry experiments. So we have considered the following criteria for judging the greenness of potential new experiments. Like they should reduce lab waste and hazards. It should illustrate green chemical concepts. It should teach modern reaction chemistry and techniques and can be accomplished during a typical lab period, and should use inexpensive greener solvents. So like just one example from the monograph I just want to share with you. This is the liquid CO2 as a green extraction solvent. So we are just going to extract D-limonene from the orange peel. You know, the extraction requires the organic solvent, but all the organic solvents are very toxic, highly volatile, fire hazard, costly. And see, liquid CO2 is non-toxic, non-inflammable, and chemically benign. And for the students, they know that it's a solid, it's a gas also, but how can it be used as a solvent? So we can show them by using phase diagram to at different temperature and pressure. You can see this is the phase diagram. Now this experiment requires very few things like a polypropylene tube, a coiled copper wire, dry ice. You know, you can get from any ice cream stall and orange peel. So what to do? The procedure is a copper wire was taken and coiled at one end, and a piece of filter paper was fitted in between the coils like this. A copper wire was taken, coiled at one end, and piece of filter paper was fitted. Then a polypropylene centrifuge tube tapering at one end was taken and the wire was fitted inside it. So you can see the polypropylene tube was taken and wire was fitted inside it. And then the orange peel was grated and using a cheese grater and put inside the tube. So orange peel grated and put inside the tube. Then this was topped with crushed dry ice and sealed with a plug seal cap. And then the tube was put inside the plastic cylinder containing water at temperature 30 to 50 degrees Celsius. So you see what happens. Just the demonstration of that. This is the tube coming, water and dry ice is melting. You can see here, this is the dry ice is melting, converted to liquid CO2, and liquid CO2 is circulating through the orange peel. Extracting limonene from orange peel. Yeah, so you got the orange peel, limonene from orange peel. This is time, affordable, safe, effective, and convenient. And what you can extract natural product also from coffee, fruits, flowers, and spices using the same method. Even you know, BSc also invited me on live in file. You know, the pharmaceutical industry is larger waste producing industry. So what we did, so what we did, we had written or edited a book on hazardous reagent substitution for pharmaceutical industry. And this book was published as a green chemistry series by Royal Society of Chemistry. Then on the basis of the popularity of this book, I was invited to act as a series advisor to the editorial board. This is a very popular green chemistry series of Royal Society of Chemistry. Even just in 2019, I was awarded or a Newton Fund workshop to organize the Indo-UK workshop on green chemistry for societal needs, healthcare, pollution, and circular economics. So this was the Indo-UK workshop. You can see the participants, and this was fully funded by the British Council and Royal Society of Chemistry, London. So around 25 participants were invited from UK and around 30 were from India. You can see this. Then recently in the Nexus newsletter published by ACS, they have given we have an international student chapter at University of Delhi. So they have highlighted. It is a very popular Nexus newsletter of ACS. So they have highlighted about our work, our research group's work. These are my research students. Even in 255th ACS National Meeting at New Orleans, they have invited me and my students to attend this meeting. So we have attended, they have funded that travel and other things. Even one of my students conference every year organized by American Chemical Society, and this is the best conference on green chemistry and engineering. So in 21st ACS conference, my student now, she is assistant professor in Hindu College, Delhi University, awarded the best poster award. We got a Green Chemistry Award from American Chemical Society, University of Delhi ACS student chapter, and got $5,000 to organize international activity. So we had organized a workshop on greening on our education system. And these were the workshop organized, and you can see Dr. Mary Kichoff was the chief guest from, she's director, American Chemical Society's Green Chemistry Institute. Then recently we got a grant of $915 to organize the ACS Symposium series. This is in November we are organizing. So this is the last slide. I just want to show you that whenever we are going to start a reaction or we take a material, we are always considering properties, these properties of material: state of matter, color, melting point, boiling point, solubility, electrical conductivity. And the day when we will add these two also with these toxicity and impact on environment, that day I will stop delivering lecture on green chemistry, because chemistry itself will be green. So thank you very much for your kind attention, and join us in this mission of popularization of green chemistry. You can join us. There is no fee, nothing is there. So that's all from my side, Dr. Bhuvan.
Thank you so much, sir. Thank you so much for your so nice and valuable informative lecture. I think our participants learned many things, and now they learn many things how Green Chemistry Network Center works, and they organize so many different conferences and organize symposium. I'm requesting all the participants, please follow the website and in future workshop and conferences as well, and then please participate in those, because we will definitely learn many things from those organized conferences as well. And I'm requesting on behalf of Akal University, sir, please provide us or guide us or give us some opportunity to organize such a conference offline mode, so that we can organize in collaboration with ACS or RSC. So for that, we need your kind support. Thank you, sir. So now I will, if any participants wants to interact with sir, please raise your hand. Or if you have any question, then please, yes, if free, please Yes, please unmute and start
Hello.
your video as well, please.
Hello.
Yes, madam, can you please start your video?
Dr. Bhuvan, I'm not in the setting
Yeah.
where I could start my video. I'm so sorry. Is that okay?
Okay. Then you can ask question.
Good afternoon, Dr. Rakesh, sir. Sir, I'm really inspired by your work. And my name is Ifra, and I am a MTech student of Aligarh Muslim University, and I'm looking forward to pursuing my PhD from the United States. And the topic that I'm interested in would be green chemistry, and I was really confused, what topic to go for and what is the recent trend. So after your presentation, I'm really inspired by this work, and I would really love to explore this more and more. And so far I've attended so many presentations, but in your presentation the unique quality was that you focused on, you not only presented your work, but you also identified the gap where the research is to be done. So this is extremely inspiring, and I would definitely love to collaborate with you if there's ever an opportunity with you. So thank you so much.
Thank you, Ifri ma'am. Now I'm
Thank
requesting
you.
Manira
Dr.
Sharma ma'am.
Bhuvan, I can see. Dr. Bhuvan, I can see Professor
Yeah, Ansu
there.
Dandia. Yeah, Ansu Dandia ma'am is also from the past lectures, and we are very much thankful to her from the past lectures. She attended all the lectures, and she has a lecture also at the 4 to 5. Thank you so much, ma'am. Yes, ma'am.
I would like to speak something. Actually, I'm feeling proud to be associated with Professor
Professor
Sharma.
Dandia, thank you. Yeah, she is helping a lot. She is the co-editor of a journal, Current Research in Green and Sustainable Chemistry. She is with us. This is published by Elsevier. So she is helping us a lot.
Well, it is really my pleasure to listen you. So many times I have heard your talk, but it is very interesting, very inspiring, and it is my pleasure to work with you. And I look forward for some other opportunity also. Really,
thank you, Professor Dandia.
Yeah.
Good afternoon.
Thank you. Thanks a lot.
Thank you, ma'am.
I also wanted to thank you, sir, because I'm really stressed to choose my topic to pursue the study in the PhD. Now I'm choosing the green chemistry, greener approaches a lot preferable topic for me.
That's great. I could even one or two students are inspired by my lecture. That's great. That's I'm able to do something. It's good.
Thank you
You
so
are
much.
really inspiring, sir.
Thank you.
Yes, Dr. Shashadhar Maji, please unmute yourself and start your video. Yes.
Thank you, sir, Professor Sharma.
Yeah.
Basic concept of green chemistry, an extensive contribution in the field of green chemistry were explored by this nice lecture. Thanks, sir. My question or my query is, if hazardous materials are employed to produce valuable compounds such as drug, maintaining high atom economy or other green criteria, then it will be treated as green chemistry. At a time, 12 principles are not followed at a time to produce the valuable compound. But my basic question, sir, what will be the minimum criteria?
You know, I've shown the definition of green chemistry.
Yes, sir.
Either reduce or eliminate. It's not all the 12 principles are followed. Go say
Not audible. Not audible.
minute. Dr. Bhuvan.
Yes, sir.
There's some problem with the, I think, internet connection.
Okay, yeah,
Not audible.
now I think there is some connectivity problem. There is Professor Dr. P.K. Chaturvedi, sir. Sir, if you have any questions, because you raised your hand.
Yes, sir. Yes, sir. I asking a question. I am running the industry. If I product a lot of amount of the sanitizer, but why to remove the smell of the IPL? And if you added to the water is develop the germs. So how to remove the activity of the water produce germ?
Yeah. So, Dr. Chaturvedi, can you hear my voice?
Yes. I listen you well. I listen well.
Yeah. We have created a green chemistry network center. So
I developed the sanitizer basis of the green chemistry, but I mixed the terpenes to remove the smell of the IPL. But
I can understand that. But the problem is this: I am not expert of all these things. That's why I created.
Thank you. Lot of things.
Yeah. So what I suggest. So please listen me. What I suggest, you send me the problem associated so that I can circulate that problem in my network. And we can suggest the best solution.
Yes, sir. If you after the pandemic condition, the demand of the sanitizer is high, but the sanitizer based on the IPL, but smell is unaffordable and pollute the environment. So, basis of the green chemistry, I mix in the terpenes and glycerol and hydrogen peroxide. So they remove the smell of the IPL, but in addition, of water is necessary. So water is the.
Sir, Dr. Chaturvedi, you please, share your problem with sir through mail, and you please write the detail. I think the sir will definitely help you to solve this problem. So now, is there any other participants who want to interact with sir, because this is a good opportunity for you, and any PG students who wants to pursue PhD and wants to do some research with any green chemistry or liquid nitrogen, liquid carbon dioxide, especially, so you can approach to sir for the for your PhD after qualifying NET. So thank you so much. This is a good opportunity for you people also. Now, any other participants wants to interact with sir, please, or you can share your views also, because it is already 12:27. So sir is already almost 2 hours task. So thank you so much, sir. If there is no questions, so dear participants, we will again meet at 1:45 p.m. For our 9th lecture. So thank you so much, Professor George Keklevic from Hungary. He will Budapest University. He will deliver his lecture. So thank you so much. Please take lunch, because under this pandemic situation, we can't offer you the lunch also. So definitely we will organize such conference offline mode, and that time we will arrange all these things. So thank you so much once again, dear participants. We will meet again at sharp at 1:45. Thank you so much. Thank you so much, Professor Sharma. Thank you so much, sir. Thank you, sir.
Okay. Thank you.
Thank you, sir. Thank you, Ansu, madam.